Why learn SQL? Well, databases are everywhere. Every time you select a name from your smartphone address book, you're using a database. If you conduct a search online, you're using a database. When you log into your network at work, you're validating your name and password against a database. Even when you use your ATM card at a cash machine, you are using databases for PIN number verification and balance checking. What this all means is that whether you are running reports, building smartphone apps, or creating websites, you're more than likely to be going to use a database as part of the project. And if you need to work with databases, then you'll most likely be using SQL to do so. After all, SQL-compatible databases are the most commonly used and deployed databases. Now, SQL, pronounced SQL or SQL, stands for Structured Query Language, and it's been around since the 70s. SQL is an easy language to learn. It contains far fewer language elements than other programming languages, and all statements are clearly named, making their use obvious and intuitive. But don't let that simplicity fool you. SQL is an incredibly powerful language, and by mixing and matching statements, there's no limit to what it lets you do with the data. Now, this video series won't teach you everything you need to know about SQL. Rather, it focuses on the statements you'll use most often, explaining and demonstrating their use, and incrementally adding functionality and complexity. And by the time you're done, you'll have the skills you need to work with any major database management system and the foundation on which to keep improving your SQL skills. Welcome to Lesson 1, Introducing SQL. As its title suggests, this lesson introduces the SQL language, and in doing so, also reviews important database terms and concepts. And the objective is to either jolt your memory if you already have some database experience, or to provide you with the absolute basics if you're new to databases. Understanding databases is an important part of mastering SQL. We'll start with a review of basics including terms like table, row, column, keys, and briefly discuss what relational tables are. We then talk about how to choose a DBMS and what you'll need to follow along, trying the examples for yourself. So let's start with some database basics. Starting with the word database itself, there's a lot of confusion around the word database. A lot of people misuse the term. So what is a database? You know, if you ask the average database user what database they're using, they'll tell you Oracle, SQL Server, and so on. That's actually incorrect. A database isn't the software that runs a database, that's a DBMS. A database is a structured store where data is located. You can kind of think of a database a bit as a filing cabinet. If you're storing information in your office, you wouldn't want individual files laying around on the desk and on the floor and in stacks and places. You want a structured place where they all can be stored and managed. And the database is just that. It's kind of like the filing cabinet. What manages the database is the DBMS, and this is what people often call a database. DBMS means database management software. And examples are MySQL and its shoot-off MariaDB, Postgres, DB2, SQL Server, and so on. And so data is stored in a database. Now, again, using our file cabinets analogy, when you're putting files into your file cabinet, you don't just toss them all in a drawer. They go in individual files. And the file folders can be thought of as tables, right? If you're putting papers in a file cabinet, you wouldn't want to throw your customer information and orders and invoices all in the same place. You need a separate folder for each. And that's exactly the role tables play within a database. A table is very structured. It only contains a single type of data. You'd never store product lists, for example, in the same table as you saw customer info. And so a database is made up of lots of tables. And in this example here, you can see a series of 5 tables. This is a screenshot from a view in MySQL, but just about every other database will have a similar view where you can see your tables. Here you can see there's a table for storing customers, a table for storing orders, a table for storing individual order items, and so on. Within the table, there are columns. And columns are the specific parts of information that are stored. So in a product table, you might have a column for product name, price, vendor, and so on. And in a contact table, you'd have individual columns for first name and last name. When a table is created, the columns are individually defined. Every column has to have a name, and the name is unique. It describes what it stores, first name, last name, and so on. And every column will have a data type, and the data type tells the table what type of data can be stored in it. If you're storing numbers, it'll be a numeric type, and that'll prevent you from putting letters A, B, C into that column. If it's going to store an order date, for example, it'll be a date data type. The data type is really important, and we're going to see lots of examples of those later. And then there are other optional details that might be provided when creating the table to specify what the column is and how it works. Right? So the table then stores the data in individual columns. And here is an example of our customer table, and you can see it's got a series of columns. There's a customer ID, name, address, they're all broken out individually. And the general rule is any data that you might want to access specifically should be in its own column. And most database administrators are very careful to have as many columns as they need, erring on the side of too many perhaps. Individual records that get stored in the table are stored in rows. Rows are the data records. And you could think of these, again, using our file cabinet analogy, as the individual pieces of paper that get put into a file folder. When a record is added to a table, a row is added, and then data is stored in each column for that row. And here's an example, again, of the same customers table. And you can see there's a series of rows, name, address, some of information, some don't. Okay, let's talk about relational databases. SQL is a language used to work with relational data. So we need to talk about relations, tables, and what that actually means. In a relational database, data is broken into lots of individual parts, each stored in separate tables, and they're connected to each other. These connections are called relationships, and thus relational database. And SQL, as we said, is the language that is used to work with relational data. Now, here's an example of 5 tables. It's actually the tables we're going to be using for all the lessons throughout the series. And you can see they're related together. So for example, there's a customers table, there's an orders table, and an order is placed by a customer, and so order relates to customer. And then orders has items in it, and so order items relates to orders. And then within order items, there are products, and that relates to the product table. And a product is made by a vendor, and so it relates to a vendor table. And this is very common. This kind of diagram is a relationship diagram, and it's often used to explain how tables relate to each other. So how do these relationships work? What is it that glues these tables together? The truth is, they're not glued together. There is no actual fixed relationship between them. Relationships are virtual and created as needed. And the way they're created is using keys. And keys are really important, and there are 2 kinds of keys that are used in relational tables. The first is a primary key. A primary key is simply a way to uniquely identify every single row in a table. And so if you have a customer list, every customer will have a unique number that will never ever change. List of products, every product will have a unique number, and so on. It's really important to have primary keys. Unfortunately, they're not required. It is entirely possible to build tables and use them without primary keys, and that practice is really frowned upon. It creates all sorts of problems later on. Assume that every single table has to have a primary key that uniquely identifies each and every row in the table, and this will become really important when you see how we work with the data in later lessons. The other kind of key is a foreign key, and a foreign key is a link from one table to the next. And if that sounds a little strange, let's look at that diagram again. So let's look at the customers table. You see that little key symbol by cust ID? That's the symbol that's telling us that customer ID is the primary key. Every customer has a unique customer ID. Same with orders. Order number is a primary key. The order items table is interesting because there the primary key is a combination of 2 columns. The order number plus the line item is unique, right? Because you won't ever have twice 2 of the same line numbers in the same order. So those are all primary keys. Look at the orders table. Customer ID there is a foreign key, right? The customer ID is referring back to the primary key in the customers table. And that's what links the 2. And so when we want to know which customer played this order, the order number in the order column, the customer ID, is that foreign key refers back to the primary key in the customers table, and that's how these tables are related. So primary and foreign keys are really important, and we're going to be using them a lot in future lessons. Now, to use SQL, obviously, you're going to need a DBMS or access to one. If you work for a company, if you're in school, your hosting company might actually already have a database server you can use, and you'd have to ask for permission to use it, get access, and use the software to go with it. Or you can install a database of your own, and I strongly encourage you to install one so you yourself can try all the lessons here as well. I mean, SQL is a language, and the best way to learn a language is to actually use it. The important thing about DBMSs is that they fall into 2 broad categories. There are client-server DBMSs and shared file DBMSs. And the truth is, the SQL we're going to learn throughout this series applies to both, for the most part. But there are some important differences. In a client-server database, like MySQL, Oracle, SQL Server, there are actually two parts to the database. There's the server software that is running on a server somewhere. It might be actually on your own local machine, but it could be on a server somewhere, it could be remote, it could be hosted. And then there's client software. That's the software you use to actually type in your SQL and enter commands. And the client software connects to the server. In a shared file database, those are really one and the same. Shared file databases are things like Access and FileMaker. And they sit locally on your machine, and you can actually write SQL in those and use them. However, there's some very serious limitations to the SQL that is supported by shared file databases. And so, as a general rule, those would not be ideal for learning SQL. You really want to go with a client-server database. And there are some really good ones, including free ones. MySQL, MariaDB, PostgreSQL, as examples, are free, open source for the download, and you can try those and learn with that. Now, if you are going to install a client-server database, you're going to need an editor. Now, this is important. SQL, as I said, is a language, and so it's plain text. It's actually written in English. You could write SQL in any editor you want. You could write it in Notepad or any other editor, and then submit it to the database server, DBMS, for processing. That's generally not a good idea. Most client-server databases come with clients specifically made to simplify your work with SQL. They do things like color code your SQL syntax, and you'll see a lot of examples of that in future lessons, and it's really useful for being able to read and debug SQL code. They give you a way to test your code right inside the development environment and display results. They let you browse through tables so you don't have to remember every table and column name and you can see them. They have built-in help and more. When you install a client-server database, it might not install the client by default. As we said before, client-server databases are often installed where the server is in one location and the clients are elsewhere. And so often when you install a client-server database, like MySQL, Oracle, or SQL Server, it installs the server without the client, and the client is a separate install. Either way, you're going to want that client, and if you do opt for a local install, which I do recommend, make sure you do install those local clients. You are going to need them. Okay, with that, you're ready to start learning SQL. You should have a database installed, client-server preferred. And if you want to follow along, all of the examples used throughout this series, and download scripts for all the examples for free so that you can populate your own database, Oracle, SQL Server, MySQL, Postgres, whatever you're using, and set it up so that you can follow along with all of the examples used in these lessons. Now that we have reviewed the necessary basics, we're ready for Lesson 2, Retrieving Data. In this lesson, you learn the single most used SQL statement, the select statement. You learn how to use it to select individual table columns, multiple columns, every column, and just distinct rows. We also discuss SQL compatibility, or rather incompatibility, and use data limiting as an example of this. And finally, as this is the first look at SQL, we use the opportunity for you to learn and refine some important SQL skills and best practices. It's time to learn our first SQL statement. The statement that you're going to use the most, and indeed 10 of the lessons in this series are dedicated to it in some way, shape, or form, is the select statement. Select is used, as its name suggests, to select or retrieve data from a database table. You type in a select statement, and it needs, at a minimum, 2 pieces of information. What it is you want to select, which columns, and where you want to select it from, so the table. Now I'm going to show you a syntax over here, and I want you to pay attention to this screen because we're going to be looking at a screen like this repeatedly over the next 10 lessons. The select statement starts off really, really simple, as you see here, select a column from a table. But as you add clauses to it, it can end up being dozens, even hundreds of lines long. And there actually is a very strict order to how select has to be used, what clauses come in what order, and how keywords are used. And so each time we introduce a new part of the select statement, you'll see a screen like this one that shows you the order they have to be used. Now, they're not all required, but they still, if are used, have to be used in a specific order. For now, select column from table. Let's look at a simple select statement, one that will retrieve a single column from a table. So here's an example. Select, and the column is product underscore name or prod underscore name from products. Now, we're going to run this code inside of a SQL editor so you can see what it does. Okay, this is SQL Server Management Studio. This is an example of a client. This is the client user of SQL Server, and if you're using another client, it'll look somewhat similar. A couple of things to notice. Usually there's a large editor window. This is where you type in your SQL. And I'm going to put some SQL in right now. And you can see there's the code. Now this is the color coding I mentioned to you before. The beauty of color coding is it makes it really easy to see if you make a mistake. Look at, for example, what happens if I mistype the word select. Notice how the color changed. That's a real quick and clear indicator to tell you there's a problem. And there are lots of different colors like that. You'll see constants are in black and variables in red and so on. This is the SQL Server color scheme. Oracle, MySQL, others color things differently. But they all serve the same purpose. The idea is to let you very easily see code and find errors. And it's really important when your code gets longer and longer, and it helps you organize it properly. Now, the other thing you'll notice is here on the left is an Explorer bar. This lets me see what's in my database system. So here is this database I'm using called TYSQL. Here are the tables, and I can actually expand and see the columns inside them. And again, your client editor might have the tool laid out a little differently, but they all provide the same basic functionality. They also have the ability to run your statement. And so when I'm done, I hit execute, and it connects to the database, and there are the results. And it might not be very clear on the screen, but what it's done is this SQL statement has been submitted to SQL Server. SQL Server has processed it, gone to the products table, got all of the rows, and returned product underscore name for each. It's a really simple example. And we could just as easily pick a different column, just change the name, and execute it again, and you'll see different results here as well. This is the simplest SQL statement, selecting one column only from a table, and all rows are being returned. So returning one column with a SQL select was pretty easy. How do we select multiple, 2, 3, or more? Well, it's no more complicated. You simply list all of the columns, and they have to be listed in a comma-delimited list. Here you can see 3 being selected. Let's again go back to the editor and take a look at that. So here's our example from before, select prod underscore ID, and I can hit comma and say something like product underscore name. You'll notice how the editor has actually given me help and shown me the available columns as well. Most IDEs will do that. Now if I execute it, I get 2 columns, and I can add a third one. The columns will be returned in the order that you specified them, and the individual column names must be separated by commas and no comma after the final one. The important thing is you can list as many columns as you want, as long as each one is separated by a comma and no trailing comma after the last column name. If you have too many or too few commas, you will get a SQL error. But what if you want to return all columns in a table without having to list each one individually? Maybe there are lots, or maybe you don't even know the names of all the columns. There is a shortcut, and it looks like this. Instead of individual column names, I can say select star. Star is a wildcard. And if I run that, it returns every single column in the table. Now this may seem like a really simple solution, just always use select star, whether you need all the data or not. That's actually a really bad idea. The primary reason it's a bad idea is that's making the SQL Server work harder than needed. Now in our example here, I'm using a local database and it's just me, and there are 5 very small tables with not a lot of data. But you can imagine bigger production databases with hundreds of tables and millions of rows of data. Select star is going to return a lot of information, and if you don't need it, you're A, making the database work too hard, and B, sending a lot of data over the wire between the client and the server. That's very efficient and is considered a really bad practice. So as a general rule, select star is there. It's a useful tool for playing with SQL. There are times you might actually want all of the data. As a general rule though, don't use select star, and do specify exactly the column names you want. There's actually another really important reason to do that as well. Imagine if a database administrator changed the name of a column. If you were specifying column names individually, you'd know right away. You'd refer to a column name and get an error message that it doesn't exist. If you did select star, you would get every row back again, And other code, your client, your app on your device, your website, something else might break because you would be referring to columns that no longer exist. Another reason that generally not to use select star in production. It's there and it's really useful when digging into databases, but SQL users generally try to avoid it in production database use. So far, the select statements we've used have retrieved all rows. That's usually what you want. But what if you want only distinct rows? Let me show you what I mean. Here, select vendor ID from products is returning 9 vendors. There are 9 vendor IDs in the product table. If you look at the first 3, they're actually the same because that vendor creates 3 products. What if you wanted a list of just the vendor IDs without any duplicates? You want distinct values. Well, you can do that by adding another keyword to the select statement. And this is a really good example of how you can incrementally add clauses and keywords to SQL to get it to do different things. So here I'm going to do distinct, and notice how it color codes again to let me know I spelled it correctly. And if I run select distinct vendor ID, it's only going to return distinct values, no duplicates. And this time only 3 come back instead of 9 because each vendor created multiple products and therefore there are fewer of them. Distinct is optional. If you don't use distinct, obviously all rows get returned. If needed, you can also limit the number of rows that come back. Now again, this is not overly useful in our examples here because the tables are very small. But you can imagine a table that has thousands or millions of rows and you're doing some simple testing to see if your statements work or how select is working. You wouldn't want all that data returned every time. And so there is a way to limit the result sets. It's not used that often, and the main reason I'm showing it to you is to point out something really, really important, and that is that not all SQL implementations are the same. So let's first look at how you could limit retrieve data in SQL Server. So SQL Server lets you say, for example, select top 5 product name. And if I execute it, I will get no more than 5. That's just one example you could do. There are other ways to use top to get just the data you want. More important, though, is how this would look in another database. This time, let's look at how it would look in MySQL. So here's MySQL's version of the same statement. And here, select product name from products, limit 5. Very different syntax. If you try to use the limit 5 syntax in SQL Server, it'll throw an error. If you try to use the top syntax in SQL Server in MySQL, it'll throw an error too. And if you're using DB2, Oracle, there's going to be even yet different implementations. This is very DBMS specific, and that's an unfortunate reality. While SQL generally is a standard language, once you start using more advanced features, it becomes a little less so. Honestly, I don't remember the last time I used top or limit myself. They're not that frequently used. More important is just keep in mind that as you're playing with SQL, you may see an example that works well, and you try it and it doesn't. And the reason it might not is you might be using a different DBMS. Really important to consult the documentation because SQL, unfortunately, is not as compatible as we would like. Before we finish our discussion of the basic select statement, I'd like to review a few other important topics that you should be aware of, things that are just useful to know to refine your SQL skills. The first one is the use of whitespace. Simply, whitespace is ignored by your DBMS. And you can use indentation, line breaks, alignment to make your code more readable. For example, these 3 statements will all do the exact same thing. And the fact that they are on 1 line or 2 lines or 4 lines really makes no difference at all. Let me show you that in the development environment. So here's a simple select statement. You've now seen this multiple times, and when it's executed, it returns the results. I could put them all on 1 line and execute it, and the exact same results. I could do some strange line alignment. There's really no good reason you'd ever want to do this, but it's legal, it's valid SQL. If you hit execute, it runs again. You can use whitespace as you see fit. And the examples we've been using are short enough that they could fit on 1 line. Most SQL developers like to align the clauses so you can see them clearly. Not that important yet, but as you start getting more complicated SQL, and some of the lessons we're going to look at soon have dozens and dozens of lines of nested code, whitespace, alignment, lining up clauses with each other, indentation will become really useful and a really good way to manage your code properly. You also probably noticed that every select statement we used thus far was terminated by a semicolon. This actually is not required in the examples we used. but it is best practices, and here's why. The examples thus far have been a single statement: type in the SQL, run it, and get results. It is possible to run multiple statements, and when you run multiple statements, they must each be terminated, separated by a semicolon. And so if you're going to copy code back and forth between different SQL scripts, it can be really easy to not have a semicolon because you copied it from another page that didn't have one, and then your SQL is going to break. Most SQL developers are really strict about this and make sure that every single SQL statement is appropriately terminated with a semicolon. Even when it's not needed, does no harm, always good to put it there. The other thing to keep in mind is that SQL is, for the most part, case insensitive. Now here, to make it easier to read, I've been using SQL keywords like select and from in uppercase. I've been using the actual columns and tables are in the database to match properly, so mixed uppercase and lowercase. You can actually use any case you want. Some developers like everything in lowercase, and for the most part, SQL is completely case insensitive. Now, there is a possible exception to that. Some databases, depending how they're configured, might not be case sensitive for SQL statements, but might be case sensitive for the object names. And so words like select and from, you can mix and match case. But the names of a table and names of a column, you might not be able to. Really, the only way to know that is to ask your database administrator how it was configured or try it out. Probably more important than all of that is be consistent. If you're going to write SQL, you're going to come back and look at it in a week, a month, a year. Someone else is going to look at it. It's going to be a lot easier if there's consistency across your code. So decide what's comfortable for you, all uppercase, all lowercase, as we've done here with uppercase for keywords, lowercase for objects. It's fine. Pick what works for you and be very consistent and use it. In this example in the slide here, you can see the same statement multiple ways. The first is the example we've used thus far. Then you got it all in lowercase, all in uppercase. Those are all fine. They will all execute exactly the same way. And finally, you want to use comments. Comments are used to describe your code. And this is something all programmers do. If you're writing in any language, C, C#, Objective-C, Java, anything, you probably put comments in your code. It's a good practice to do. There are two primary reasons you do it. One is to describe your SQL so that when you come back later, you know what you're doing and why. Again, simple select statements, probably not that critical, but as the complexity grows, it becomes very critical. The other reason is an interesting one. It's what programmers call commenting code out. And I'm going to show you an example of what that means. Here are two simple comments, two common ways to use comment syntax in your SQL. The first one is an inline comment, and you can see here it got colored in green so you can see it was a comment. And that is to have two dashes followed by a comment. These can go inline. And so on the first two lines of code, the fact that the second half of the first line is a comment, that's ignored by the DBMS, and what will be executed is select product name from products. The second example is a more interesting one, because here I was experimenting with two SQL statements. The first was select product name, comma, vendor ID from products, and the second was select product name from products, and going back and forth between them. And I didn't want to execute both. By putting the comment designators around the first one, I commented out the code. And so if I run it, that block of code, the first two lines will be ignored, and only the select statement that's not in a comment will be processed. And this is a really good way to play with code without having to delete it and copy paste and save it elsewhere. You can leave comments in your code, comment out as you needed, and most developers find this a very useful tool for playing and tinkering and modifying their code. Let's summarize this lesson. Select is used to retrieve data from a table. It's a really important SQL statement, and the reason I decided to teach it first is it is the one you will use the most. We also dedicate most of the lessons in this series to select. Select can return one or more columns. Results can be limited as needed. We also review some best practices. Use whitespace to make your code more readable. Use lots of it, as much as is comfortable for you. Comment your code. Lots of it. More comments, the better. And finally, be consistent with how you use case. Pick what works best for you. Use uppercase, lowercase, whatever is comfortable for you to work with. Whatever it is, use it for all your code and be consistent with it. Thank you. This is lesson 3, sorting retrieved data. We introduce the select order by clause and cover sorting by a single column, sorting by multiple columns, as well as specifying sort direction. When you retrieve data from a table using select, in what order is the data returned? Well, the answer is it's up to you, and if you don't specify how you want data to be ordered, then really there's no way to know. The information that we retrieved so far in our sample select statements were probably returned in the order they were added to the table, and that's pretty typical on a brand new table. But over time, that may not be the case. Think of how pages will be added to a book. Each time you're adding a row, you add a new page, and then at some point in the future, you delete some rows, so you're deleting a few pages, and then you add a few new ones again. The DBMS is going to try to be very efficient in how it uses space, and so it'll insert new rows into space that had previously been used by other rows. And so what happens over time is as you work with your table, add, modify, update, delete data, suddenly the order where information gets returned to you could be anything, really no way at all to know. And so if you want data to come back in a specific order, it is up to you to specify it. And in a select statement, you do that with the order by clause. Order by tells the select statement how you want information to be ordered. You tell it the column to sort by, and you tell it sort direction possibly. And we're going to look at those. Now, you'll recall that I said that we're going to keep adding clauses to the select statement. And as we do so, I will keep showing you the syntax because it's really important to get the clauses in order. So here's the select statement revisited. Select column from table, and then order by column. If you have an order by clause, it must come after the select and the from. If it's before select and from, you get an error message. And we're going to keep looking at this select statement each time we add additional keywords and clauses. But let's take a look at order by. Let's start by ordering data by a single column. The code looks something like this. Here, select product name from products, and we're ordering by product name. And so this will return a list of product names from the products table, and they'll be sorted alphabetically by product name. Let's take a look at that in the tool. So here is our select product from products statement. We've seen this many times already. I'm going to add another line here. And notice I moved the semicolon down, otherwise my order by would have come after the semicolon, it would have been its own clause. And here I'm going to type order by prod name. And again, you'll see the color coding for me to tell me I spelled it correctly. And now if I execute it, this time the results are sorted alphabetically. Now, interesting, you can actually sort by columns you're not retrieving by. Take a look at this example. Instead of ordering by product name, I'm ordering by product ID, and now when I execute them, I'm returning the product names, but the order that they're sorted in is the product ID in the table, even though I didn't actually retrieve product ID in this select statement. You won't often want to do this, but it's important to know that you actually can order by anything. You can order by any column in the table, whether you're actually using it in your retrieval or not. Now you can also sort by multiple columns if you want. For example, if you were retrieving contacts from a contact database, you may want them sorted by last name, and within last name by first name. You can do that too, also using the order by clause, and it looks like this. Just like when you provide a list of columns to a select statement, those columns need to be comma delimited. So too when you provide a list of columns to an order by, they're comma delimited. And so here we're selecting product ID, name, and price, and then sorting them by price, and within price by product name. Let's take a look at what that code will do. Here's the same code, and if I run it, it returns 3 columns, and they're sorted by price in ascending order, and there are several that cost $3.49, but within that price, they're listed by product name alphabetically. Simple example of using multiple columns to sort in an order by clause. I want to show you a variation of this order by clause. And I will preface it by saying that I really would rather you don't actually use this when you're writing your own SQL code. This is a shortcut that a lot of developers like, and I'll show you why. Here, we're retrieving product ID, price, and name, and we're sorting by the second column and the third column. And so a shortcut would be to replace product price with 2 and product name with 3. And this is basically telling SQL that when you order by the second retrieved column and then the third retrieved column. In this case, 2 becomes product price and 3 becomes product name. And if I execute it, the results are exactly the same. So why do I not think you should use this? Well, think about it. Imagine you had a really long SQL statement, 50, 100 lines long, so long that when you're looking at the columns at the top of the select, you're not looking at the order by at the same time. You've got to scroll to see them. At some point in the future, you add another column to your select statement, or you make a change there. Without knowing, you've changed the sequence the order is going to be returned simply because you added another column to the select statement. A lot of really good SQL statements have broken and apps have misbehaved because of this shortcut. I understand why developers like it, but really the saving is not worth it. The reason I show you this is I want you to know what it is. You will see this used in examples online, in books. A lot of code generators generate code this way because it's simpler. And I understand why. It is less code, but it's too risky. And honestly, it's not worth the risk of breaking code in the future for saving a couple of column names. I'd much rather your statements be explicit, specific, and not run the risk of breaking in the future. But if you see it, you'll know what it is. The order by clauses used thus far sort alphabetically or numerically from 1 and increasing from there. So product prices start lower, then go higher, and product names start at A and go through Z. If you need to sort in descending order, you can do that too. And the syntax is very simple. You just add the descending, D-E-S-C, or you can spell it out descending, keyword to the order by. So here, order by product price descending. Let's take a look at this in the editor. So here is a SQL statement that by now should be very familiar, retrieving 3 columns sorted by price. And because they're sorted by price, the lowest price one comes first, the highest price one comes later. And I can add descending over there. And now if I sort them, the most expensive one comes first, and then comes the less expensive one. Now you can actually mix and match sort sequences. So if I wanted to, for example, sort in descending price order, but then within each one by name alphabetically, I could do that. So I'm going to add product name and now run the statement. And this time it's going to sort by price, but within each price, the name is alphabetical. And you can have as many columns in your order by clause as you want, and each one can explicitly be listed as ascending or descending. You actually can specify ASC for ascending if you want, but typically you don't, because the default order, if descending is not specified, is in fact ascending. Okay, let's summarize. Within select, you use the order by clause to sort retrieve data, and you can sort by 1 or more rows. When you sort, you can specify a sort sequence, either ascending or descending. If you don't specify any sequence, ascending is the default. The best practice is to never rely on the default order that rows come back from a table in a select statement, because you really don't know what you're going to end up with. So best practice is to always have an order by clause. And avoid using column positions in order by. Lots of developers have suffered painfully for having done so. When you retrieve data from a database table, you seldom want every row in that table. In Lesson 4, Filtering Data, we start the discussion on the select where clause. We learn where clause operators, how to use between to filter for a range of values, as well as how to use null to filter for no value. So far we have looked at using select to retrieve 1 or more rows and then sorting the results using order by. Next we need to look at filtering data, because you usually don't want to return every row in a table. Usually you're looking for something specific, looking for a particular customer or all products in a certain price range or an order or so on. To do this in a select statement, you use the where clause. And where gets added to select, and where takes really one piece of information. And that is a statement that defines a condition for what rows to be retrieved. The where clause statement is evaluated against every row. So if you're looking for a price, the DBMS will look at that price, match it against every row, and return true or false. And for any that are true, the row is included, any false, it's not. Now, as promised, we're going to revisit the select statement, and we'll keep doing this because order within a statement is really important. If you're using a where condition, it has to come after the from and before the order by if you have one. You can use where condition without order by, but if you are using both, they have to be in this order. Select the column names from the table, your where clause, followed by order by. If you don't have it in the right order, it'll throw an error message. The filter statement passed to a where clause can contain operators like these. You can use equal to test for equality. For non-equality, you can test for not equal, or the combination greater than, less than, which equals the same thing. Less than, equal to, greater than equal to, the standard mathematical operators you'd expect. We'll look at a couple of examples here, and then let's look at it in the development environment. Here, we're selecting product name and product price from products for any products with a price of 3.49. This is going to tell the DBMS to search, find those products, and return only those. In this example, we're looking for products made by any vendor other than the vendor specified. Now, the reason I'm showing you this example is to point out something very important. Look at the value passed to compare to vendor ID, DLL01. Notice how it's in single quotes. When you pass literal values to a SQL statement, if they're strings, they need to be enclosed in quotes. In the previous example, there were numbers, so you didn't need to do that. But here, DLL01 is a string. Strings have to be in quotes. If you don't specify that quote around it, if we would have said where vendor ID not equals DLL01, the DBMS would have thought you were referring to a column called DLL01, which doesn't exist, and you get an error message about that. By putting single quotes around it, you're saying it's a string, and that's the string that's being compared to, in this case, compared to see that it does not match. And you're going to see this in examples as we go forward, but remember, whenever you are passing a string to a SQL statement, whether it's in a where clause, or later on you're going to see it when you're inserting and updating values, strings must be enclosed by single quotes. Now, for this reason, you want to make sure you're not typing your SQL statements in word processors, because word processors like Word, for example, will change quotes to what they call smart quotes, which actually are a different character. And if you copy and paste a SQL statement out of a Microsoft Word document, for example, and embed it into a SQL Server editor to run the script, it'll actually throw an error message because it won't know what to do with that quote. You need real quotes, and that's another really important reason to use IDEs made for SQL statements, because that way the quotes will always be exactly what you need. And if they're not, well, they'll color code and you'll see it's wrong. Okay, let's look at some of these examples inside a development environment. Okay, this is a SQL statement inside MySQL Workbench, the IDE used with MySQL. And if I execute it, it returns the rows that have a price of 3.49. Now, notice the color coding here is a little different. As I mentioned in a previous lesson, different IDEs will color code differently, and the exact color coding is not that important. What's important is that it actually is color coded. The other thing worth noting is that when it comes to numbers, you may have to deal with decimal spaces. And for the most part, the DBMSs will try to do that for you. So for example, if I'm searching for 3.49000 and I search for that, it still finds the ones that are a price of 3.49 because that is the same number. Unlike strings, where strings are matched exactly, numbers, the DBMS is going to be smarter for you and it'll try to figure out what it is you want. Now there's an interesting side effect to this, and that is if you actually insert the number with decimal places, what you get back in a select statement might be different. Different DBMSs will default differently to how many decimal spaces they provide, and there are ways to control that, and we'll talk about that in future lessons. Okay, here's our next example. Here, we're selecting all products that have a price of less than 10. And if we retrieve it, we'll get it back again. Now notice that I didn't have to worry about the decimal point over there. The DBMS handled that for me because it knows the number and it's doing all the proper number arithmetic. If I wanted to do less than or equal 10, it's just a less than or equal operator, and I'll get, this time, no extra ones because I are not priced that way, but you get the idea. I want to show you one last simple example, and that is not testing for non-equality. Here I'm using a combination less than and greater than symbol, which means not equals, to return any rows that are not made by the specified vendor. This is actually functionally identical to doing this, not equals, and that would do the exact same thing. Different DBMSs support one or both of those operators, and you can use whichever one you want. If needed, you can also filter by a range. For example, what if I wanted to find all products that were priced between $5 and $10? For that, I can use a special operator called between. Here's what the code looks like. Select what I'm selecting from table, where the column name between one value and the next value. Now, there are actually other ways to do this as well, as we're going to see in future lessons, but for now, let's look at what this code would actually look like if you ran it. Here's the example in MySQL Workbench. If I run the example, it returns all of the items with the price within the specified range. And between is used to specify two values, the lower one first and the greater one second. Between can actually also be used for dates, and you can specify a first date and a second date to find rows that have a date range between those values as well. And this between is inclusive, right? So anything that matches 5 and 10 will be included, not just values between 5 and 10. Sometimes you may want to filter for rows that have no value. Now, what does that mean? No value doesn't mean the column is empty. Like, for example, in a contact table, somebody doesn't have a middle initial, and therefore maybe the middle initial is blank. In SQL, there's a difference between an empty column and a column with an empty string. An empty string means it's actually a string but there's no value in it. In SQL, an empty column is considered a null column. Null means there's actually nothing in it at all. A null is a special keyword that you could use in where clauses to find or exclude columns with no value. And let's look at a couple of examples of that, because this is actually really important and something you're going to use very often. Here, I'm looking for the names of all products that have no price. And that's obviously not going to return anything because all the products have a price. So not an overly sensible example, but important to note that it's actually valid SQL. You can say I want all columns that have a null in them, and if there are no null, nothing will get returned. Let me show you a more useful version of this example. Perhaps on the contact list, you want to send out an email. And so because you're sending out an email, you need all of the contacts that have an email address. Those that have no email address are going to be null in the cust email column. And so here, if I return them, I'm finding only 2 of my customers have email that is null, so those I would not want to include. Right? If I say is not null, those are the ones I would want to include in my email. So you can test for is null or is not null. Notice though that I'm not using equals here. Unlike mathematical operators and string operators where you use equal, greater than, or less than, when testing for null, you use is and is not. But the result is the same. If you're testing for is null, you will find only the rows that have a null value in a specified column. If you're saying is not null, you'll find the ones that don't have a null value in a specified column. Okay, let's summarize. Within a select statement, use where to filter data, and where must be provided a condition. You can use operators to test for equality, greater than, less than, null, and so on. If you're working with strings, remember to always put single quotes around your string, otherwise the DBMS will assume you're referring to a database object as opposed to a string. And finally, let the DBMS do the filtering for you. And where clauses can get tricky and can get very complicated. Depending on what you're looking for, you can construct some very sophisticated where clauses, as you're going to see in the next couple of lessons. And some SQL developers end up retrieving all data, pulling it down to the client tool, and doing the filtering on the client. That's generally a bad idea. DBMSs are very good at filtering. They're very efficient. They have optimization engines that are designed to really make filtering very fast, very efficient, and they're always going to do it far quicker, far more efficiently, and with far more resource usage than if you're doing it on the client. So as a rule, you always want to filter on the server and only return back to the client the exact data you need. We're going to look at where clause filtering in greater detail in the next few lessons. Welcome to Lesson 5, Advanced Data Filtering, which continues the discussion of the very important select where clause. You learn how to combine where filters using and or, and discuss order evaluation and how to explicitly manage this. We then look at using in-list to filter using a defined set of possible matches, and clause negation using not. Simple where clauses in SQL select statements just test for equality, not equality, greater than, less than, and so on, as you've seen. If needed, you can combine clauses to create more powerful where clauses. And the way you do that is using and or. With and, you're specifying multiple conditions in your where clause, and all of those conditions, 2 or more, must be true. If my where clause has 2 conditions separated by an and one is true and one is not, that condition will not be met and the row will not be retrieved. And all conditions have to be true. Or is the opposite. When you use an or, you're saying either this or that, either condition is true or they both can be true, and then the row will be retrieved. Now let's look at a couple of examples of what that means. In this first example, we're looking for product ID, product price, and product name from products, where a vendor ID is specified as a string, DLL01 is a string in quotes, and the product price is less than or equal 4. So if vendor DLL01 has a product that costs more than $4, it's not going to get included. And if another vendor creates a product that costs less than $4, it also won't be included, because both of those conditions must be met, must be true, in order to return the column. In this example here, we're looking for product name and product price from products where vendor ID is DLL01 as a string, or vendor ID is BRS01 as a string. So if either of those conditions are true, either of those vendors, the row will be retrieved. Right here, either condition has to be true. And in this example, it's actually impossible for both to be true because they're both compared against the same column. Let's look at a couple of these examples inside the development environment. Here's our first example, this time using an AND. Only rows that match the vendor ID and the product price, both conditions must be true, those will be returned, otherwise they won't. In this case, 3 rows were returned. And just to show you, if we would have made that an OR, this time an extra one was returned, one more that had the right price match, but from a different vendor. In this example, we're going to use OR, so either of those conditions need to be true. And if I execute, it'll return all of those products that match either the first clause, vendor ID is DLL01, or the second clause, vendor ID is BRS01. It's worth noting that where clauses like this could get very long very quickly and very hard to read. Going back to our comments about whitespace in the previous lesson, what a lot of SQL developers would do here was put that OR on its own line indented like this. And this way, the where clause is easier to read, it's cleaner, and you can clearly see that the line following the where is part of the where because it's been indented. You can also combine and OR clauses. But when you do so, you've got to be really careful about the order they are evaluated in. Now, to demonstrate the problem, let me show you an example. Let's say I wanted to find all products made by one of two vendors, either DLL01 or BRS01, and they all have to have a price of greater or equals to 10. Doing those individually is easy. To find all of the vendors, we could do something like this. This example here will return all the vendors that have a vendor ID of DLL01 or a vendor ID of BRS01. And then if I wanted to find only products from DLL01 with a price greater or equal to 10, I could put an AND over here like this and execute them, and this one actually returned no products, but that is valid SQL. Now what if I wanted to combine them? Take a look at this example over here. Here I'm getting product name and product price from products, where vendor ID is DLL01 or vendor ID is BRS01, and the price is greater or equals to 10. And if I run it, it returns the rows, but look at the results. Of the 5 rows, 4 of them are actually priced less than 10. That obviously didn't work. Even though I'd given it a clause of and product price greater or equals 10, it found the ones priced under 10 anyway. Why did that happen? Well, we have to introduce a concept here called order evaluation. When SQL processes where clauses, it first processes the ands before the ors. And so even though we wrote this as where the vendor ID is DLL01 or vendor ID is BRS01 and price is greater or equals 10, that is actually not how the DBMS read it. What it read it was vendor ID is DLL01, end of clause 1, or the vendor ID is BRS01 and price greater or equals to 10, which means all products from vendor DLL01 are going to be included regardless of price. Obviously, that's not what we wanted. Right? Ands always get evaluated before ors. So how do you solve this? Well, the way you solve this is by using an order evaluation that's higher than and that's the parentheses. So here's how it works. I can start a parentheses over here and end it over here, and this is now telling the DBMS, first evaluate the parentheses. So vendor ID needs to equal DLL01 or BRS01. And then for all rows that match those, then apply the AND. And now if I execute it, the results are correct, right? So let's make this very clear. The order of evaluation is parentheses always come first. After all parentheses have been evaluated, then the DBMS will evaluate any AND clauses. And after any ANDs, it will evaluate OR, which means you can use parentheses wherever you want to force a higher level of evaluation. And the truth is, many SQL developers always use parentheses, even for a really simple where clause, where column equals value, they'll put parentheses around that clause just to avoid ambiguity. And then as their where clauses grow in complexity, they just add parentheses and nest them. It's generally not a good idea to just rely on the default order of evaluation and assume that because AND is before OR, things will work the way you want. It's a good idea to always use parentheses and be very explicit about the order of evaluation. If you think about it, when you're filtering with OR conditions, you're actually filtering for one of a list of values. If you are looking for vend ID equals something, or vend ID is something else, or vend ID is yet something else, that's really vend ID equals one of these three choices. And so SQL gives you a shortcut for specifying these kind of OR lists. And that's called filtering with an in. In is used to specify one or more values that need to be matched, and they're comma delimited, as you see here. Here, in and in parentheses, 1, 2, or 3 would actually be the equivalent of 3 OR clauses, each one testing for 1, 2, or 3. And let me show you an example of how this would be used. Here, we're selecting product name and product price from products, where vendor ID is in a list of two things. The first is a string, DLL01, and the second is a string, BRS01, and then it's ordered. And if I execute it, it works properly. Now, the truth is, this is exactly the same as if I would have used an OR instead. And if I replace that with an OR, the results will be exactly the same. In is just a shortcut for using OR. So why bother using in? Well, there are a couple of really good reasons. The first is it actually would have solved the order evaluation problem previously, because you weren't actually using an OR, using an in and an and it would have worked by default. Secondly, if you have a long list of ORs, if you're only using 2 of them as we're using here, it's probably not that much of a saving. But imagine you had 10, 15 of these. Over and over again, vend ID equals first option, vend ID equals second option, over and over again. That'd be really, really long. And it'd be much simpler saying vend ID in and just give it a list. And so there's a simplicity and shortness of code value as well. There's actually a third important reason to use it, and that we're going to talk about in a future lesson where we discuss subqueries. If needed, you can also negate where clauses. That means you can make a where clause do the opposite, as in not. Here's how it works. If you want to look for products that have a price other than 3.49, instead of saying where product price equals, you can say where not product price equals. Now, if you're thinking there are easier ways to do this, you're right. Let's look at a couple of examples. Here we're selecting all products where the vendor ID is not, where not vend ID, equals DLL01 and ordering them. And if we execute it, we get all the vendors other than that one specified. Now, the truth is, this is exactly the same as using the not equal operator that we saw previously. And if we check for not equals, it'll return the same things. And you can even negate the not, which isn't overly sensible, but that's legal and it'll work. So why would you ever want to use not? Well, the truth is, in our example here, it's not that useful. Where not becomes very useful is with in, because in is looking for a list of things, and so you can put not before it. Also, when working with subqueries and some more advanced SQL topics we're going to learn later. Okay, so let's summarize. Within a where clause, you can use and to combine conditions, in which case they all need to be true. You could use or to provide conditions where one or more needs to be true. Both can be true. And is always evaluated before or, and that can create some interesting problems. And so parentheses are used to explicitly define the order of evaluation. If you have a long list of items you want to search or against, you could use in, and you can use not to negate any other where clause. And a best practice here, as we already said previously, is always use parentheses to avoid ambiguity. Don't always assume that the DBMS is going to do what you want. If you can provide the parentheses, less risk of it misbehaving. We continue looking at the where clause in lesson 6 using wildcard filtering. We introduced the like keyword and learned 3 wildcards that you can use to search for any character combinations. As you've seen, SQL Select makes it really easy to test against actual values, equality, non-equality, or and so on. But what if you want to search for partial values? What if, for example, you need to find all products that had the word cat in the middle of it? Obviously, there's no equality or non-equality search that can test for that because you're not looking for a string or a value. You're looking for a partial string or a partial match. To do this, the SQL Select statement lets you use search strings with embedded wildcards. And there are 3 wildcards you can use, 2 of which are very compatible, 1 of which is a whole lot less so. Let's take a look. To use wildcard characters, you use your where statement like before, but instead of testing for equals or not equals or so on, you test for like. Like is a special keyword that tells SQL that what comes after like is a string that is to be used as a wildcard match as opposed to a simple equality match. So like followed by a search string. And the search string is then made up of regular text you want to search for with special characters embedded in it that have special meanings. If you put a percent in there, for example, percent means match 0 or more characters, whatever they may be. Underscore matches a single character. And these 2 are actually supported consistently by every DBMS, with the exception of Microsoft Access, which makes you use a asterisk or a star instead of the percent character. The other wildcard you can use is a set, and that's with square brackets. This one is actually not that commonly used. It is available if you need it. SQL Server does support it, for example. MySQL does not. Now let's take a look at a couple of examples of these. You can use wildcards anywhere in a string. This first example here has a select statement that's looking for product ID and product from products for any product like fish %. Now what this means is the text that matches has to begin with the word fish, but it can follow by anything. It could be nothing after it, it could be spaces, it could be additional text. Because the wildcard character is at the end of the text, anything afterwards can match. If you want to search for a word in the middle of a string, you need 2 wildcard characters, 1 at the beginning, 1 at the end, as you can see here in the second example, where like, %, beanbag, %, if beanbag is at the beginning or the end, or if it's the entire string or anywhere in the middle, it'll match, because wildcards at either end match 0 or more characters, whatever they may be. The underscore works similarly, but unlike the %, which matches 0 or more, underscore matches exactly 1. And so here, if we're searching for underscore space, there better be 2 characters before a space, otherwise it won't match. And we'll look at examples of this in a second. Let's take a look at these inside the editor. Okay, we're in MySQL Workbench, the editor used to work with MySQL. I'm going to put in a simple statement, one we just saw. And here we're looking for products where product name like, and the string has a wildcard at the end. And so if I execute this, it finds just the 1 because it begins with the word fish, but regardless of what comes after it. Let's try replacing that wildcard with one that uses 2% characters, like this. So here it's going to search for any text, could be no text at all, beanbag, followed by any more text. And if I do a search, it found 3, all of which had that text in the middle. Now, you could also use a wildcard in the middle as well, just by itself. Let's take a look at one example of that. Okay, let's replace that search string with a new example. This time, the text has to start with the letter F, ends with the letter Y, and it can be absolutely anything in between. And it found exactly one example. Now, I should caution you one thing over here. There are some databases, some DBMSs, that append spaces at the end of text to their fixed length. So if you had a column, for example, that was supposed to be 20 characters long, and you save a string that's only 8 or 9 characters long, it might actually pad them with spaces, in which case this search would have failed because you're looking for ending with a Y instead of ending with a space. For this reason, a lot of SQL developers will always append a % at the end just to be able to handle any padded spaces. And so it would look something like this. And now if I do the search, it'll work even if there are trailing spaces as well. I want to show you one more type of wildcard. But this wildcard is not supported by MySQL, so let's switch over to SQL Server for this one. This wildcard uses square brackets. And what this is saying is match any of those characters. So it's going to look for a contact that starts with a J or an M, that's an OR, followed by any character. This is two wildcards, a set wildcard and then an any character wildcard. And if I execute it, it finds any of the contacts that begin with the letter J or the letter M. Now this can be negated, as you've seen before, right? You can put a not in there and it'll find any of the other ones. But actually you can also negate right inside of the set, which may be simpler if you're working with more complex operations. And the way you negate this kind of wildcard is with the character in there like that. And that means anything in this set, exclude it, look for anything but that. And that functions exactly the same as the not you saw previously. So we've seen three wildcard characters, two which can be used very consistently across all databases, the set one less so. The truth is, if you need really complicated expression mapping, there's another way to do it, and that's using regular expressions. Now, regular expressions, or regex, is a very complex subject unto itself. There are entire books written on the subject, and it's beyond the scope of this lesson. It's also not supported by all databases. Regular expressions is its own language, a language made entirely for searching for text. And it does some pretty sophisticated things like look for a character, but no more than a certain number of characters away from another character, or only look for characters that are preceded by something or have a certain character after it as well. Look ahead and look behind and more. Regular expressions are supported by some databases. Oracle supports them, MySQL supports them. They're not the subject of this lesson. If you do want to learn about regular expressions, you can pick up a book like my own, Sam's Teach Yourself Regular Expressions in 10 Minutes. But wildcards are really important, and they're really important for searching because they give you incredible flexibility. That flexibility, though, comes with a cost. And to understand the cost, think of how you would search through a book to find something. If you had a book and you wanted to find a particular topic, you would turn to the index at the back, browse through in order, find whatever topic you want. It tells you what page to go to, and you would find the page. If that index wasn't there, or if you were searching for something that was not indexed, you would have no choice but to go through page by page by page in the book, reading all the characters to find matches. And that's kind of how wildcards work. If you're searching for something that begins with the letter A, that's pretty easy for the DBMS to find it. It uses an index and it finds A quickly. But if your search string is wildcard followed by text followed by a wildcard, there's really no way to index that data because the search could be anywhere inside of any text, which means the database, the DBMS, is going to go through the table column, every single row, do a substring search, do the match, and find the rows for you. And on small tables, that's not a big deal, but on large tables, that can be very, very time consuming. And so wildcards can actually be very, very slow to use, which is why you don't overuse them. But when you need them, they're invaluable. Okay, let's summarize. If you want to do a wildcard search, use a like instead of an equality test. Generally, the percent wildcard, which matches 0 or more characters, or the underscore wildcard, which matches exactly one character, is supported by every major DBMS. Brackets, less so. Some best practices: don't overuse wildcards, especially not at the start of a string. That's actually the worst place to use them. At the middle of the end doesn't have the same resource impact, but at the beginning it can have huge implications. And finally, if you are doing searches and you are worried about trailing spaces, wildcards are a great way to handle those. This is Lesson 7, Creating Calculated Fields. Calculated fields, also called derived columns, allow you to create logical table columns as needed. To introduce the concept, we start with a concatenation example, and then we look at aliases, as these are needed to name and use calculated fields. And finally, you learn how to perform on-the-fly mathematical calculations using calculated fields and mathematical operators. The next topic to discuss are calculated fields, also called derived fields. Now, we haven't used the word fields before. Best way to think about it is field is just another name for a column. When you see the word field, word column, use them interchangeably. A calculated field or a derived field is a field that doesn't actually exist, or a column that doesn't actually exist in the table. Rather, it's one that's programmatically generated on the fly. Now, why would you want to do something like this? Perhaps, for example, you want to return a order summary, and in the order details, you've got the product price and the quantity, and you want to return the extended price, which is quantity times price. Or perhaps you're going through a contact list and you're doing a mailing, and you want to return, instead of city, state, zip, country, you want to concatenate these fields together and turn them into something suitable for a mailing label. There are lots of reasons why you may want to manipulate data, put it together, and create new calculated or derived fields that get returned along with your results. We're going to show you how to do that in this lesson. And we'll start off with concatenation. Now, concatenation is arguably not the most useful example, nor the most common one, but it's an important one to understand, and I'll show you why. Concatenation is used to append columns to each other. So if you, example we just gave of the mailing list, and you want to take city, state, zip and format it and concatenate it into a single field. Pretty simple thing to do, but also very incompatible. Look at this example over here. SQL Server lets you use the plus operator. You're just adding them. So here we're adding the vendor name as an example, followed by an open parenthesis, and notice it's in single quotes because it's a string, followed by country, followed by another closing parenthesis. If you're using Oracle or SQLite, DB2, Postgres, you can't use plus. You have to use the pipe character, the two vertical lines. If you're using MySQL and MariaDB, those don't allow you to do any operations on strings that way, and there's a function called concat that you pass values to. And the exact differences between these are less important. I'll run a couple to show you what they do. What's more important is how you use these, as you're going to see. Let's take a look at this concatenation example, both in SQL Server and in MySQL. So this, once again, is MySQL Workbench, and you can see we've got a select statement, and we're using a function called concat to concatenate a name, a string, another column name, and another string. And don't worry about functions just yet. We're going to talk about them a lot in a future lesson. But if I execute this, what it returns is a single column that is exactly what we asked for. It's the vendor name with the vendor country in parentheses. Look at the name of the column, though. How would you refer to this column if you wanted to use it in your SQL? That's what we're going to get to in a moment. But first, let's run the same example as well in SQL Server. And SQL Server, as I told you, makes it really easy. You can just use plus to concatenate. And if I execute here, you get essentially the same result. They're concatenated. Concatenation isn't the most useful example of a derived field, but it does demonstrate the point very well. Here we're working with a derived field, a calculated field. It doesn't actually exist in the table. It is created, derived from other columns, and a new field, a calculated field, is created that gets returned to us with the result set, and it can be used like any other column in the table. The tricky thing, though, is how to actually use it, and that's what we're going to look at next. To use a derived field or a calculated field, you need a way to name it. You've already seen in a select statement, you have to refer to column names if you want to retrieve them or use them in a where clause or order by them. These derived columns, these calculated fields, have no names. They don't exist in a table. They're created on the fly when we need them. To name them, we use aliases. And aliases are a way to give something a temporary or virtual name for the duration of the execution of a SQL statement. And there are several reasons you might want to use an alias. You're going to see soon one example is tables. Now, there are rules about how tables should be named, but imagine if somebody named a table with a space in it. That's technically, it is legal, but it creates real problems in a SQL statement, because as you've seen, a space will be treated as a next clause. And so there are ways around that, but one solution would be to temporarily rename the table for a duration of a SQL statement. And you're going to see an example of that when we talk about joins in a later lesson. You can also alias columns, as you're going to see over here, and calculated fields. So how do aliases work? So here's the same three code snippets before for each of SQL Server, the Oracle DB2 implementation, and the MySQL implementation. And in each of them, I've added an as keyword after the column. This is basically saying what you're selecting, when you select it as what I'm naming it as, and that's creating an alias, creating a temporary name. Now let's take a look at what this does in practice in the code. This is the same SQL statement, selecting the vendor name, open parenthesis, the vendor country, close parenthesis, as vendor underscore title. There is no column in the table called vendor underscore title. And yet if I execute this, you'll see we have now a new column called vendor underscore title. This column was created specifically for this statement. It was derived off other columns. It's a calculated field, and it can be used on your client side like any other column. And this is really useful, really important. And again, concatenation is probably not the best example of aliases, but it's a nice simple one. Let's move on to a more important use for aliases. You can also use calculated fields to perform mathematical operations. And of course, you can use an alias to then name the results of that operation for use in your result set. Select statements can perform the operations you'd expect: addition, subtraction, multiplication, and division, and these are the symbols you would use. When you perform a calculation, you can use other columns, multiply them, do whatever you need. The key is that if you want to use the result in a returned result set, you then name it as an alias, as you just saw before. Let's take a look at an example of this. Here we're retrieving all of the order items for order number 20008. We're retrieving the product ID, the quantity, and the item price. Let's execute that. And we get back 5 rows. You can see 5 of this item at 439, 10 of that item at 349, and so on. Now, what if I wanted to also return not just the quantity and the price, but the extended price? That is how much this entire set of items costs by multiplying the price by the quantity. I can do that by adding a calculation right inside of this query. Here the select statement has been updated, and so notice we added a comma because we added another column. I also broke them over multiple lines now because it's reaching longer than the length of a single line. It would be hard to read. But look at this fourth column. It is quantity times item price as expanded price. And so now 4 columns are going to be returned. Prod ID, quantity, and item price are actual columns in the table. Expanded price doesn't exist in the table at all. It's going to be calculated on the fly, calculated for each row, and returned as a derived field. And if I execute it, there you get the extended price as well. Calculated fields make it really easy to perform mathematical operations on columns, and the important thing is the alias, which then lets you actually use it. To summarize, calculated fields, also called derived fields, are a way to perform operations, usually mathematical operations, on other columns. Things like concatenation, mathematical, anything you need. The key is if you actually want to use the results of that calculated field, you need to name it. And so we introduced aliases. You're going to see aliases used in other ways later to rename tables, for example. But here aliases are used to name a calculated field. And when you use an alias, you specify it using the as keyword. Welcome to Lesson 8, using data manipulation functions. We already looked at functions briefly in Lesson 7, but here we review them in detail, explaining what they are and how to use them. We start with string functions, as these are the ones you'll use most, and then we move on to date functions, which are frequently used, but which are also the least compatible between different DBMSs. Our next topic is the use of functions. Now, you've seen an example of functions already. I showed you one in passing in the last lesson, where I showed you concatenation in MySQL that used the function concat. That's a rather unusual use for functions, but functions are very useful. And you're going to see lots of examples of them in this lesson. The unfortunate thing about functions is they tend to be the least compatible part of the SQL language. And string functions will be a little simpler, but when I show you date and time functions, honestly, none of the functions are compatible with other DBMSs. And that's an unfortunate reality because using date and time manipulation is really, really important. But we'll look at some of those examples. And we'll start with string functions. Common functions are things like left, right, or even substring. These let you extract parts of a string. For example, if you wanted to get the middle initial from a middle name, just the first character. Length, to get a length of a string. Lower and upper, to convert strings to lowercase or uppercase. Some implementations call it L case or U case, but it's the same thing. And one of the most useful set of string functions are the trim functions. And these remove any trailing or opening spaces. So ltrim trims white space from the left of a string, rtrim is from the right side of the trim, and trim removes from both sides. Let's take a look at a couple of examples of these. We're going to start with a simple string function, upper. String functions tend to be some of the most commonly used functions. They're also really easy to use and very compatible. Here's an example. And here, we're returning the vendor name, and I'm converting the vendor name to uppercase. Now, obviously, there's no practical use of this example, but it does demonstrate the use of the upper function. And notice how in the editor, functions get color-coded with a different color, again, to make them easy to identify, easy to look for misspellings, and so on. And if I execute it, I'll get the vendor name twice, once in regular case and once in uppercase. Now, I'm going to show you a really useful little trick when it comes to working with functions if you want to figure out what they do. And I will preface this by saying this works in every single DBMS besides Oracle. Oracle does not let you use SQL without a from clause. All others do. And here's an example of why you might want to do that. There's a string function called soundx. Soundx is really interesting. What it does is it turns any text, any string, into a code that represents the sound of that string. Now, soundx has nothing to do with SQL. Soundx exists in other applications too. It's a pretty well-defined format where any string can be turned into a 4-digit combination of strings and numbers that represents its sounds. But look what I'm doing here. Here I'm selecting the soundx. So soundx is a function of the name Michael Green, and it returns this set of characters over here. Now, that's really useful. Why? Because what if I wanted to know if the soundx would work to match something like this? Michelle Green, and do an execute, and it returns the same result because they both have the same soundx value. When you're playing with things like strings, numbers, and you want to know what the functions will do, all databases, again, minus Oracle, will let you do a select and play with those functions right in line to see the result. But let's actually use this soundx example that I just showed you. So if I was looking for that name, and I do a search, and it found no rows because the name doesn't exist. But if I search for the same string, this time using a soundx, this is saying, don't just find Michael Green, but find anybody who might sound like him, because maybe I put the name in a database and forgot the name slightly or mistyped it. So here it's going to do a soundx on the contact and a soundx on the name, and if they match, it returns them, and sure enough, it returned the one value. It's a really nice example of using string functions and also how you can use select to play with those functions to see what they actually do. The other functions that are really important to understand are date functions. And by date, I mean both date and time, because when dates are stored in tables, the column data types are usually date and time and store both. Working with date is really important. If you want to sort or extract all the invoices from a certain year or find records between a certain date range, if you want to find the delta between two dates, those are all very common operations. Unfortunately, the date time functions are the ones that are really, really incompatible. Now let's look at a couple of examples. Some of the common uses for date functions are things like extract parts of date or a time. So perhaps you want to return the day of week for a date, or the month or the year, comparing values as we just said. Another really important use case is formatting the dates, right? If you're going to format a date for display in the US, you're going to display month, day, year, whereas in Europe you might do day, month, year. And if you're specifying the date spelled out, then the actual text of the date is going to be very different depending on what country and language you're working with. And the date functions handle these. They can handle all the kind of formatting you need, but again, as noted, they tend to be incompatible. As an example, these SQL statements here are trying to find all the orders that were placed in year 2012. SQL Server has a function called datePart, and datePart lets you pass in a date and what part of the date you want. YY for year, MM for month, and you can get the day of week, the hour, the minute, the second, or so on. And so date part of YY of order date will return the year part of a stored date, regardless of what else is in it, regardless of if it's a full date or a date time, and compare it with 2012. Oracle doesn't do that at all. It forces you to take the date and extract the year part of it, and then convert it to a string, which you then have to convert again to a number to be able to compare it to the number 2012. And that may look a little convoluted, but actually it gives you a lot of flexibility, but yes, there's extra work for you. When it comes to date functions, nothing can beat MySQL or MariaDB. They have a whole library of functions, including year, which returns the year, and there's month and day of week and so on. The truth is you can perform these kind of operations with any DBMS, but as you can see, the exact SQL syntax varies greatly from one implementation to another. Now, let's actually look at these examples inside both SQL Server and MySQL. Here's MySQL, and as you can see, we're using the year function to extract the year from order date and compare it, and if we execute, we get all the orders placed inside that year. To do the same thing in SQL Server, we would use the datepart function, and again you can see datepart is color-coded because it is a function, and we're asking for the YY, the year in it. You'll also notice that as you move your mouse around in SQL Server Management Studio and put the mouse over objects or functions, you get a little tooltip help to tell you what it expects. And here we're using datepart to extract the year and compare it, and if we execute it, we get the results. Okay, to summarize, the data manipulation functions are really important, and you're going to be using them throughout your SQL statements. String functions, you're going to use them to compare strings, extract strings, convert strings, and more. And they generally are pretty compatible. There are minor differences, but for the most part, they work the same in most DBMSs. They're the date and time functions, probably the most important ones, and also the ones that are unfortunately the least compatible. You are going to have to refer to your own DBMS documentation because, as you've seen, there are significant differences between the DBMS implementations. There are also numeric functions to do things like financial calculations. Those tend to be used a lot less. We're going to be using functions a lot more in the upcoming lessons. Thus far, we have used select to retrieve rows from tables. Sometimes you'll not want all the rows. Rather, you'll want summarized data, totals and averages and so on. In Lesson 9, Summarizing Data, you'll learn how to do just that, looking at the aggregate functions, average, count, max, min, and sum. In Lesson 8, you learned how to use functions. There's another set of functions that are really important, and these are aggregate functions. Functions that are designed to help you summarize data. For example, what if you wanted the total of how many products were in your inventory? Or if you wanted the total price of an invoice? Now you could just retrieve all the products or all the items in an order and send all that information down to the client and then use whatever tool you're using to loop through and generate the results. But the truth is, that's wasteful. If you actually don't need all the data, why would you bother retrieving all the data? What you really want is the summary of the data. And that's where aggregate functions come in. The aggregate functions operate against a column or part of a column and return a value based on it. So average returns the average of values in a column. Count returns how many there are. Max returns the highest value. Min the lowest value. And sum adds them, totals them, returns the sum. Now there are some important differences in how these are used, and so we're going to look at some examples. The average is pretty easy. Select average product price as average price. This, as you'd expect, will return one row with one column with the average price. Count is a little different. Count can either take a column name or it can take star. Now, if it takes a column name, as in the second example on the screen here, it'll return the total number of rows that have a value in them and exclude the rows, not count the rows, that are null. If it's star, it'll count all rows even with null values. Max does exactly as you'd expect. It returns the highest value in a column, and interestingly, a value need not be a numeric value. Max could also return the highest alphabetical value, so whatever is the last value when sorted alphabetically. Min is the opposite, the earliest, and it will return the lowest value, either numeric or alphabetical. And finally, sum. Sum does exactly that. It totals things. And here you can see sum quantity. So it'll return the total items, total quantity of items in order 2005, but sum can also be used with an aggregate function. So here it's going to add up the total price of the order for each row, multiplying item price by quantity, and then using sum to aggregate all of those. That's pretty impressive. So let's take a look at how this actually works when you run it inside of the IDE. we'll start with average. Here, we're selecting the average product price for all products in the table. And if we execute, you get the average price as listed over there. Now, obviously, you could use where clauses here. And if you use a where clause, that filter is going to be applied, and the average will then be an average of only the rows that match the condition as specified by the where clause. And it goes something like this. This updated version of the statement has added a where clause at the bottom, and so instead of returning the average price of all products, it'll only return the average price of products produced by the vendor specified. And if we do a search, there's the result. Now let's look at the count function. Count, as I told you, could be used two ways. It could count all rows, or it could count only rows that don't have null values. Here it's counting all rows, count star. And so what it's going to return is the total number of rows in the customers table, total number of customers you have, in this case, 5. Now, if we wanted to know how many of those customers had email addresses, we could replace star with the name of that column, which is cust underscore email. And now if I run this, it returns 3. Only 3 of those 5 customers had an email address, the rest had null values. So count could be used two ways to count all rows or only those rows that don't have null values. Using max is pretty simple, exactly as you'd expect. This returns the greatest product price, the most expensive price in the catalog. And if you change the max to min, it'll do exactly the opposite, and it'll return the lowest priced item in the catalog. The last aggregate function to look at is sum. So here, we're adding up the total number of items that are ordered. And if we hit execute, it returns 200. So this is going through the order items for order number 20005. And for every item listed, get all the quantities and sum them. So that's a total. Now, if we wanted to get the total value of the order as opposed to the number of items, we could simply replace that and instead get the sum of the price times quantity. And if we execute it, that's the value of the entire order. As you can see, the aggregate functions are easy to use and really useful. They also have some extra features that aren't typically used. For example, this one. Here, if you wanted to get the average distinct price, so this is not averaging all of the columns, it's averaging distinct columns, as in what is the average price regardless of if a single price is used for more than one item. You can add the distinct in there. As I said, infrequently used, but if you need it, it is there. The last important point when discussing aggregate functions is what if you want to use multiple at once? If you want to get the highest price, lowest price, count, average all at once. You can, and to do that you list each of the aggregates as you would with a multi-column select. So each one is separated by a comma. Each one will need its own alias. And as you can see here, we're selecting the total number of items, the minimum price, maximum price, and average. And if I execute, that's exactly what it returns. Let's summarize. The aggregate functions are used to summarize data. To be able to use the return value, you need an alias as you've seen in previous lessons. Average, max, min, and sum require that a column name be specified, but in fact it could be an expression, so it could be a mathematical calculation used by other columns. And count could be used two ways. It could be used with a column name, in which case it counts only the number of rows that do not have a null value in that column, or it could be used with star, which then counts all rows regardless of what's inside them. This is lesson 10, grouping data. Now that you have learned how to summarize data using aggregate functions, this lesson explains how to do the same for groups of rows by using the group by clause. And then we look at having, which is similar to the where clause learned previously, but which filters by group rather than by row. In lesson 9, you learned how to use aggregate functions to summarize data. And the data we summarized was the entire table. So that if you did a count, it counted all rows in the table. And if you got the value of an invoice, you had to actually specify which invoice you want, otherwise it would value every invoice in the table. You can also use the aggregate functions to summarize not all rows, but groups of data in logical groupings. So for example, return all the invoices, but with totals per invoice. And to do this, you have to add a group by to your select statement. and group by takes a unique column name or multiple names to group by. So this is a good time to once again revisit the select statement. We now added additional clauses, so let's look at the order. Select column comes first from table, where in your condition, then the group by if there is one, and then your order by. Right, so they have to be in that order. And if you are going to use a group by and an order by, the group by must come first. So let's look actually at an example. This is going to return a row for each vendor, and then the total number of products by vendor. So count star is saying select all rows, but not all rows in the table, all rows within the group specified, and the group by at the bottom says the group is vendor ID. Now the count could have been before the vendor ID in the select statement. Order there is not important. What's more important is the group by clause at the bottom, which specifies how grouping should work, and here the counts are going to be per group. Here the group is vend ID. Let's take a look at what this code does. Here is the select statement, the one we just saw, and it's selecting vend ID and counting the number of products for each vendor. And if we execute it, we get back 3 rows, one for each vendor, and it tells us one vendor has 3 products, one has 4, one has 2. So it's the same aggregate function as before, but because it's used with the group by clause, instead of summarizing the entire table, it's summarizing for each group or each row. Now there are some important rules you need to know when it comes to using group by. You can have multiple levels of grouping if you want, and they have to be separated by commas. If you have multiple levels of grouping, then the summary will happen at the lowest possible level. So if you were grouping by vendor and then by product, you wouldn't get a summary for vendor. You get a summary of product per vendor. So if you have multiple group bys, the summary will happen at the last possible level. Every column listed in a group by must be a valid column and an expression. In a previous lesson, we talked about derived fields or calculated fields. You can't group by those. And finally, most DBMSs will not let you group by variable length columns. These are columns that store things like notes and memos of variable length. You typically cannot group by those. So you've now seen how to summarize data and how to summarize by group. But you can actually take this a step further and you can filter by group. So what if you wanted to not just get the number of products made by a vendor, but only return those vendors that make a total number of products? It's kind of like a where clause, but it's a little different. This is where having comes in, and having is just like where. But unlike the where clause, which functions at the row level, having functions at the group by level, which means once again we should revisit the select statement. So now select column from table, where and your condition, group by, and the columns you're grouping by if you're summarizing. If you want a condition on the group by, having, and the having conditions are exactly the same as the where conditions, and then followed by order by. And you can see now why we keep revisiting this syntax. As you add more and more clauses, then the sequencing becomes really, really important. So let's take a look at an actual example. Here, we're getting the customer ID and orders from orders grouped by customer ID, where having count is greater or equals 2. This is going to return all of the customers who have bought or placed 2 or more orders. If they place 1 order, they'll get excluded by the having. Now, if that expression past the having looks familiar, it should, because every expression you learned previously in how to apply to a where clause applies to having as well. And in fact, you can use both where and having, as we'll see in a moment. So let's compare where and having, because these do get confused. Where filters data before it is grouped. Having filters data after it is grouped. Now this is important, because it is possible that your where clause changes your group, right? Because if you are excluding rows before they are summarized, that could change the totals and actually have an impact on what will be included by the having later on. Here's an example, similar to the one before. It's finding any vendors who make at least 2 products priced at $4 or more. The where excludes any products with price under $4, and then the summary, the aggregate, will count how many products there are that are priced more than that, and only those that have 2 or more will be included, which means if a vendor had 2 products, one priced at $3, one priced at $5, they would be excluded. Let's look at some examples. Here, we're getting from the orders table, any customers who have placed at least 2 orders. And we execute, and 1 comes back. The count is counting the orders, the group by is specifying that the count has to happen at the customer level, and having does the filtering. This next example is retrieving vendors from the product table to see how many vendors have at least 2 products priced at $4 or more. The count counts the number of products for each vendor. The where excludes any products that fall below the $4 threshold. Grouping, group by vendor ID, ensures that the count happens for each vendor individually. And then when it has all those totals, having then ensures that only vendors that have at least 2 products are included in the result set. And finally, if you're using order by, it has to be the last of these clauses. So here we're selecting orders from the order items, and we're only finding groups that have at least 3, and they're being sorted by items plus order number. And it returns 4 rows. Okay, let's summarize. You've already seen aggregate functions used to summarize data, and group by lets you summarize at a specific row level. Now, if you want to filter groups, you use the having clause. Having is exactly like where, and so all the expressions you learned in previously and how to use them with where to filter rows, all of those apply using having as well. The difference between where and having is time of execution. Where happens at the row level before summary occurs, and having is executed against the group and excludes groups that don't meet the criteria. The combination of where and having let you do all sorts of powerful summarizing. Welcome to Lesson 11, Working with Subqueries. Subqueries are queries that get passed to other queries, and they are useful and powerful, but the length of the code involved can make them look far more intimidating than they actually are. We look at using subqueries in 2 ways. First, to filter rows in conjunction with where, and then to return a value to a calculated field. The latter use case necessitates the use of fully qualified table names, which are also explained in this lesson. We're now going to go back to the where clause and this time introduce subqueries. Now, I've mentioned subqueries a couple of times, but now we're going to look at them in detail. The best way to understand subqueries is to look at an example, because a subquery is a way to pass a query to the where clause, and so the results of one query become the search criteria for a second query. Now let's talk through a hypothetical situation. Imagine one of your products in your database is product RGAN01, and I want to know all customers who've ordered that product. Now this requires several searches, because we have to first look at which orders have that product in it. And so we have to look at the order items to get the order numbers. With the order numbers, I then have to go search to see who are the customers for those orders, and then go to the customers table with that data to find their customer numbers. So this is 3 levels of searches to find that information. With a subquery, that can be one operation. Now we're going to go through this step by step so you can see how it's constructed. So here's our first SQL statement. It's simply getting the order number for any orders that contain the specified product. And we hit execute, and we get back 2 of them. Order number 2007 and 20008. Now with that, we can find the customer IDs who ordered those. And the way we would do it would be something like this. Here we've taken the 2 results in the previous query, passed it to an in, and then we do a search and get the customers who are responsible for these 2 orders, and here they are below. Now, if you think about it, we actually didn't care about the order numbers. We only needed the order numbers to be able to convert a product to a customer ID. That order number was there simply returned by one result to pass it to a where clause to another select statement. And so we can combine those. Look at this select statement here. Here, there's a select statement within a select statement. It's selecting customer ID from orders where the order number is in whatever the results are from another select statement. Now you've seen in before. When we used it last time, it was for a simple set of conditions that were ordered against each other. And I told you then it wasn't that useful, but where it becomes really useful is when you're passing a query. And here you can see an example of that. Because here, the DBMS is going to first process the inside select statement. And wherever it returns will then get passed as a result to in the outer statement. You've got nested queries, one within another. This is a subquery. And if we execute it, we get back the results. So now let's take it one step further. the previous query returned two customer IDs. Here they are. And if I execute, I can get the name and contact. But again, the previous query with its subquery only returns two customer IDs, which in turn are being passed to this select statement. So why couldn't we take that entire query with its subquery and make them both subqueries of this query and nest 3 levels deep? Well, the answer is you can. Take a look at this revised query. Here there's a select within a select within a select. Now the DBMS is going to process them from the lowest working upwards. So first it processes select order num from order items and returns back all the orders that have product RGAN01 in it. That gets then passed to the middle statement, which gets the customer IDs for the orders as returned by its subquery. Those customer IDs are then passed to the top level query, which returns the name and contact, and it works like this. Now here you can really see the power of in, because in lets you then pass one query to another. Now the important thing for this to work, for a subquery to work, you have to remember what it's returning. What it's returning essentially is the values in a single column. And so a subquery can only ever have one column in its select. It can't be returning multiple. It makes no sense to return multiple. What would that mean when you're trying to construct an in clause? And so when you're building statements like this, it makes sense to do exactly what we did just here. Step by step, build them, working upwards, look at what they return until you build a subquery like this. Now this was a pretty complicated example, so let's look at it again. Here we have a select statement that's being passed in parentheses, and so the results of which are passed to an in statement for the previous select statement. You have one subquery returning data to a parent subquery. And then as we saw, we could take that a step further and make it 3 levels deep. And the truth is you can have as many levels as you want. The DBMS doesn't really impose any restrictions, although there are performance implications as you nest too deep. Subqueries can also be used as calculated fields. Now, the subquery we saw earlier in this lesson used a where clause to provide the results of one query as an in the where of another select statement. You can actually do the same thing for a derived column for a calculated field. And of course, you need an alias to be able to name it. Now let's take a look at an example of that. This is a simple select statement. It's counting the total number of orders for a specified customer. And if we execute, we get the result, this customer placed 2 orders. What if we wanted to do this for all customers? Well, take a look at this example. This is an unusual looking select statement. We're selecting the customer name and the customer state, but the third column is an entire select statement, selecting count from orders, and it's returning an alias of orders. Now I'm going to run this, and then I want to talk about it a little more. If we execute it, it returns a list of all of the customers with a total number of orders for each. You see 1, 0, 0, 1, and 2. Now, how did the subquery know which customer to count for? Well, take a look at this where clause. This is something you haven't seen yet. This where clause here is comparing customer ID in one table to customer ID in another table. Look at the fully qualified name. Select count from orders, that's simply counting all of the rows in orders, where the customer ID in orders matches the customer ID in customers. Orders is this table here. Customers is the outside, is the parent select statement. And this way, for each row, this select statement gets executed, matches the customer ID in the subquery to the customer ID in the parent query, and returns the results. It returns a number, the number which is in the column over here. Now, to see why this is needed, let me remove these fully qualified names. Now if I try to run it, it tells me every customer has 5 orders, which obviously isn't right. It doesn't give a syntax error because syntactically this SQL is correct. But look at this where clause. This is saying where customer ID equals customer ID, which means every time the orders are counted, it'll compare customer ID in its own table in orders, and customer ID is always going to be equal to customer ID. So basically it's going to return the total number for every row, which is not what you wanted. This is why fully qualified names are so important, and you must use them when you're using subqueries that have to refer to the parent query. Okay, let's summarize. Subqueries are queries that get passed to other queries. And the query is a select statement. It returns data. A subquery can be used in a where clause, in which case it returns a single column, which are then used the equivalent of a comma delimited list of values in an in. Subqueries can also be used in calculated fields, in which case they must return a single value only, not multiple rows, one row with one value. And when you're doing that kind of subquery, make sure you use fully qualified names to prevent ambiguity, and so that the subquery knows to match the column in one table to the column in the parent table. Relational databases are built around related tables, and tables are related using joins. In Lesson 12, Joining Tables, we review relational tables and the use of keys to perform a simple join. We look at two different syntaxes for these joins and briefly discuss the pros and cons of each. And finally, we look at joining multiple tables. Way back in Lesson 1, we talked about relational databases and primary or foreign keys and how they are used to hold tables together. We're now going to modify our select statement to join tables. And joins are really important, and they're going to be the subject of the next two lessons. Before we do that, let's briefly review primary or foreign keys. Now, tables are usually joined by keys. As we said previously, a primary key uniquely identifies every row in a table, and there can only ever be one row with each primary key value. A foreign key in a table identifies the value that's in a primary key in another table. So if you had orders and order items, the order number on the orders table will be a primary key, and in the order items table, that original order ID would be a foreign key, and that's how they're joined together. Now, what should be clear from this is that in SQL tables, we try very hard to never have redundant data. So for example, if you have an order system, you would never want to put all the customer information with shipping and billing in with every single order. Instead, you have a customer table, and you have an order table, and an order items table, and they're joined together. Redundancy is a bad thing, and not just because it wastes space, but also because it's hard to manage data. If a customer address changes, you won't change it in all the right places. A basic premise of relational database design is that information is never repeated, and you normalize it across as many tables as possible and join them as needed. Now, let's look at a really simple example here. This is the product table that we've been working with for so many lessons already. And you'll see that there's a product ID, and those product IDs, that's a primary key. So no two products will have the same value. But the vendor ID is a foreign key. And so many do indeed have the same value. Any products made by the same vendor will have the same vendor ID. As you can see, DLL01 appears 4 times. DLL01 will be the primary key in the vendors table. Now, when you're actually retrieving data, you join those tables, and that's what we're going to talk about now, joins. The simplest join simply requires 2 tables that share a key, and you test for equality. Primary key in one table, foreign key in another table. This is called an equijoin, also called an inner join, and you'll see why in a moment. This is the simplest syntax for an equijoin. Here we're retrieving the vendor name and the product name and the product price. Now, as should be clear by the column names, vendor name is in the vendors table. Prod name and prod price are in the products table. So we're retrieving 1 column from one table and 2 columns from another table. And the 2 tables are specified, vendor and products, and of course there's a comma between them. So how does the DBMS know how to join the 2 tables? The answer is the where clause. Vendors.vendorID equals products.vendorID. That creates the join. And so now the vendors and products are joined, the primary key in the vendors table to the foreign key in the products tables, and you get a unified result. This is inner join syntax, and this is actually identical to the previous example. Here, instead of the where clause being used to define the join, an inner join statement is used inside the from clause followed by an on. Now, the truth is you can use either format. ANSI standard actually prefers this latter format, the inner join format, as opposed to the simplified equijoin. However, DBMSs support both, and actually you can use whichever is simplest to you. The end result is exactly the same thing. Now, let's look at what these actually do inside the editor. Here's our select statement. vendor name from the vendors table, prod name and product price from the products table, and then joined with a where clause, joining the vend ID, which is the primary key in vendors, to vend ID, the foreign key in products. And incidentally, it's actually common practice to use the same name so you can easily see what is a primary key and what is a foreign key and how they relate to each other. And if we execute it, here are the results. One result set combined from data from two different tables. And the way it knew how to join them was the where clause. Now, just to show you how important that is, I'm going to remove the where clause. And I'm going to run the statement without any join clause at all. Watch what happens. We got back here 54 rows, every combination including completely wrong data. Here, this basically joined every vendor row to every product row. And so every vendor tied to every product, which isn't correct at all. This is actually why some people don't like the equijoin syntax, because it's too easy to make a mistake. This, if ever you do need it, is called a Cartesian product, and it is very, very rarely used. Now let's look at the inner join syntax. This actually achieves the same result as the equijoin, but this is the ANSI preferred way of coding your statements, and you choose whichever you prefer. If I execute, the exact same result. Here, the from statement itself specifies the type of join, an inner join from vendors to products, and on specifies how they are to be joined. What the inner join does is it ensures that every row on the left table is included, and only rows that are matching in the right table are included. The end result is the same thing. This is the simplest sort of join, the one we use most often, an equijoin or an inner join. We just saw the equijoin and inner join join two tables. The truth is, you can join as many tables as you want. In fact, our next example joins multiple tables. Here we're joining the order items, the products, and the vendors to return combined information to all the information you need about a single order, order number 20007. Even though that information is scattered across three tables, what gets returned is a single result set. Let's look at that in the editor. So here's the select statement. Product name comes from the products table, vendor name from the vendors table, product price from the product table, and quantity from the order items table. So we have a three-way join over here. The where clause joins products and vendors, primary key to foreign key, and then joins primary key and foreign key order items to products, and then finally there's a where clause to actually restrict to which order we want, here order number 20007, and if we execute it, here's the combined results. So now that you've seen how joins work, let's go revisit an example from a previous lesson, the subquery. As a reminder, a subquery are queries that get passed to queries. And the example we used in the previous lesson used a select on order items to find an order number, which then got passed to a select to get customer IDs, which then in turn got passed to customers to get customer information. And the results ended up looking like this. And you came back with two customers, the name and the contact. We can now recreate this entire set of subqueries with a simple join. Take a look at this join. It's selecting the same two columns we wanted, customer name and customer contact, from the same three tables. Before, each table was used in a separate subquery. And here the where clause joins them all, and the result is exactly the same. As you can see, within SQL, there's often lots of different ways to achieve the same result. And there are pros and cons to each, usually style of code, complexity of code, and performance implications as well. So it really pays to experiment. The other thing to be aware of with joins is that as joins grow in complexity, the SQL does too. And so most good development tools give you tools to help create your joins, graphically drag tables together, align them, and generate some of the code. And if possible, you may want to take advantage of these because join syntax can get rather complicated. To summarize, joins are the glue that hold relational tables together. Primary and foreign keys are needed. Primary keys on the table that has the primary value, and foreign keys relate back to a primary key. The simplest join, the one you'll probably use most often, is the equijoin, also called an inner join if you use ANSI syntax. And then as per ANSI SQL specification, that is the preferred syntax, but DBMSs support them both, and so you should use whichever you wish. In the next lesson, we're going to look at some advanced joins building on top of what we learned just here. Lesson 13, Creating Advanced Joins, continues our study of relational tables and how they are joined to retrieve data. We revisit the topic of aliases, this time focusing on table aliases. We learn about self-joins, introduce various forms of outer join, and finish with an explanation of how aggregate functions and joins can be used together. In Lesson 12, we introduced joins, the glue that holds relational tables together, and we looked at inner joins and equijoins. There are additional join types, and though used less often, they're actually really important and really useful. But before we look at those, I want to revisit a topic we looked at in a much earlier lesson, and that is aliases. Now, you will recall that an alias is used to rename a column. When we were working with derived fields or calculated columns, we use them. The as let us specify to treat this calculated value as a column name, which then can be used and returned with the result set to the user. Aliases can also be used to rename tables. And I mentioned this previously, one common use is if a table is badly named. And maybe there's legacy data and it has spaces and characters that shouldn't be in there. When you retrieve it, you can use an as, and that way you can rename it as something safe and usable. There's another reason to rename tables, and that is to give them an alias to refer to within a select statement itself. Now, this may sound strange, but let me show you an example and then show why you need it. Look at this code over here. This is selecting customer name and customer contact from customers, orders, and order items, and then the where clause joins two tables, and the third where clause is a filter. We actually saw an example much like this before. The difference here is that every one of the tables has an as and is aliased. And so customers can be referred to as C, and orders as O, and order items as OI. And if you look at the where clause, that's exactly what we're doing. Instead of where customers.customer ID, it's where C.customer ID. We've created an alias for the table and then referred to that alias name in the where clause when referring to that table. Now let's take a look at how this runs. Now, as a reminder, this is a simple alias. This is one we did in a much earlier lesson with concatenation, and there's the as, and it creates a calculated field and names it. Here we're using an alias for tables. Each of our three tables has an alias, and if we execute them, the results are returned. Now, the fact that the results were returned from tables that were referred to by an alias instead of by their actual name is irrelevant. The DBMS handles that. It knows what the alias maps do. Now, why is this important? Well, it's important for a kind of join called a self-join. A self-join is a join between a table and itself. Now, I'll show you an example of why you need that in a moment, but as you've seen before, when you're referring to tables, it's your job to eliminate any ambiguity. And if you were referring to a column name for the same table, and there were two instances of that table, the DBMS would have no idea which you were referring to. The alias lets you rename each instance. Take a look at this select statement. This is an example of a self-join. You'll notice we're returning three columns from customers, and the customers table is there twice. We're joining the two, and there's a filter on one of them. Now, the DBMS would complain that cust ID, cust name, and cust contact were unknown or ambiguous because it wouldn't know which instance of the customer table you're referring to. So here, we've used an alias to rename each one. The first instance of customers we've called C1. The second instance we've called C2. This way we can explicitly use a fully qualified table.column name in the select list, and the where clause can join them properly as well. Now, why would you want to do this? Let's take a look at how it runs inside the environment. This is a subquery. This is trying to find all customers on record who work in the same company as the customer specified in the subquery, here, Mr. Jones. And so the subquery returns a customer name, and that customer name is then used as a where clause for a search against customers itself. Notice both queries are retrieving data from customers. The inner one is returning a customer name, a subquery, that gets passed to the outer one. And if we run it, there's the result. There are two people. Now, you've seen before that subqueries can often be converted into joins, but here the subquery is using the same table as the parent query. So we'd have to join a table to itself, and thus a self-join. Here you can see we're using customers twice. We're using the second instance for the where clause to filter the customer name, and the first to get all the rows, and the where joins them together like any other relational table, and the same two results come back. Here's one more example of a multi-table join using aliases. And this time you'll notice that for the C, the customers table, we're returning all rows, but for the other tables, we have to specify exactly which row we want. Now, the reason we have to do this is there are column names that appear in both rows, as is often the case when you have primary and foreign keys. By specifying the fully qualified table.column name, you prevent the ambiguity. And so here we're joining customers, orders, and order items. All three are aliased. The select statement lists the alias.column name for each one of the columns. And finally, the where clause joins and applies the filter. And if we execute, here's the combined result. The next join we want to talk about is the outer join. Now, an equijoin or an inner join, as you've seen, joins two tables and only retrieves rows that have related rows in both tables. And so if you have a customer and an order table you're joining, and there are customers who have no orders, those customers would not be returned. An equijoin or an inner join only joins rows that appear in both tables. Now, if you want to return all of the rows in one table, for example, I want to return all customers whether they have orders or not. For those that have orders, list the orders. For those that don't. An inner join won't work for that. That's where you'd use an outer join. Now, this is what the syntax looks like. It looks just like the inner join you've seen before, but instead of an inner join, we've got an outer join, and you can preface it by saying left or right. In a left outer join, the table on the left, all rows will be returned regardless of whether they have related rows in the table on the right. The table on the right will only return rows that relate to the table on the left. In a right outer join, it's the reverse. In a right outer join, the right side returns all rows and the left side doesn't. The truth is, left and right are identical, right? So you can either use left and right or just switch the order of the tables. You'd actually accomplish the same thing. Let's take a look at how this actually runs. Okay, here is an inner join like we saw before. This is going to return customers related to orders and only the customers that have orders. If there are customers without orders, they will not get returned. And if we execute it, we get back 5 rows, the customers and their orders. Now let's change this inner join. Instead of an inner join, we're going to use a left outer join. Now this is saying everything on the left side, which is the customers table, should be returned. On the right side, the orders, only those that have rows that relate to the customers table. And now if we execute, we'll see we got one additional customer, and this one, for the order number, is null because there is no matching order. Left outer join returns everything on the left, and on the right side only matching rows. And the right outer join does the opposite. Now, there is one other kind of outer join that is very, very, very rarely used, and it is called a full outer join. And honestly, in all my years of using SQL, I've yet to see a valid use for this. But basically, a full outer join returns everything from the left table and everything from the right table, and then joins the ones that have relationships and doesn't join the ones without, which doesn't seem overly useful, but if you need it, there it is. Before we finish our discussion on joins, we should revisit aggregate functions and summary of data, because you're often going to use these together. Now, by now, it should be pretty simple how the syntax works, but it does get rather lengthy, so let's take a look at some code together. Here, we're getting all of the customers and the number of orders for each customer. Now, the number of orders are in a different table, and therefore there's a join, the inner join, and it's joined on customer ID, and then grouped by the customer ID. Let's have a quick look at how you could use aggregate functions with join data. Here is the SQL statement that's selecting customers and the number of orders for each customer by doing an inner join on 2 tables. And if you execute the results, we get the 4 customers and the number of orders for each. Now, if we wanted to include customers who have no orders, all I'd have to do is change inner to left outer, and then run it, and this time we get 0 for the one who has no orders at all. You'll notice, unlike before when we did a join where it returned a null, because you're returning a count, it knew that no rows equals 0 and put 0 in there for you. So this would be a good time to, one more time, visit our select statement. Again, select column always comes first. From table, and if there are multiple tables in a join, multiple froms. And then if you're using the ANSI SQL syntax, then you'd have your on clause for each of the froms. Group by if you're summarizing data, having if you need to filter the group, and finally orders. Let's summarize. Self-joins are used to join a table to itself. This is actually more useful than it would appear, and when you need to do it, make sure you alias the tables, otherwise it will not work, and you'll end up with all rows in both tables matched to each other. Outer joins are used to match two tables and include the rows that don't have a match in the other table. A left outer join includes everything in the left table, a right outer join includes everything in the right table, and you can actually use them interchangeably just by switching the order of the tables as well. Lesser used if you need full outer join, returns everything from every table. This is lesson 14, combining queries, our final lesson on the all-important select statement. Multiple result sets, or the result of multiple select statements, can be combined using unions. And in this lesson, you learn how to use union to do just that. You learn how to include and exclude duplicate rows, and we revisit order by to discuss how to sort these combined queries. Our last topic pertaining to the select statement is a discussion of how to join two select statements together. In SQL, this is called a union. Now, a union lets you provide two complete queries and combines the results into one result set. Let me show you how this works in the editor. Here is a really simple SQL statement. By now, you've seen this many, many times. It retrieves the customer name, contact, and email from customers and uses an in clause to specify three states here, Illinois, Indiana, and Michigan. And if I execute, it returns 3 rows. Here's another SQL statement. This one even simpler. It also returns name, contact, and email, but this time all for a specific customer as named over here in single quotes. And if I execute that, it returns 2 results. Now, what if I wanted to return one query, one result set, that combines both of those queries together? Well, I could do something like this. Look at this statement. There are 2 complete select statements here. The first selects 3 columns from customers, where the customer state in the specified values. The second select statement selects the same 3 columns from the same customers table, but this time testing for equality. And then the union in the middle instructs the DBMS to join these 2 statements and return one combined result set. And if I execute, I get back these results. Now, if you're thinking there's another way to do this, you're right. This SQL statement here does the exact same thing. Here, it's just one select statement with 2 where clauses using an or, customer state checking in 3 values, or customer name testing for equality with a specified value. And if I run it, the results are exactly the same. So why would I ever want to use a union? Well, the truth is, the union, the way we're using it here, for multiple queries in a single table, is probably not that useful. Where unions really shine is if you have different data in different tables and you want to combine the results. There's really no other way to do that. The beauty of unions is you actually don't even need the same column ordering. As each table, you can specify the columns you want, use aliases as needed, and combine the result sets. And if you have data in lots of different tables, I want to aggregate them and have one combined result set, unions are a very effective and efficient way to do just this. So let's look at the code once again. Multiple select statements and union to join them. And you can have as many as you need. Union then separates each one, and as long as the column names match, doesn't matter what order they're in, doesn't matter what table they're in, you will get a combined result set. Now, one of the things you might have noticed in our previous union example is that it automatically removed duplicates. We combined two select statements, and there was one row that matched both statements. When you did the union, the DBMS was smart enough to realize that one of those rows would have been returned twice, and it eliminated it. Unions automatically exclude duplicates. If for some reason you want all rows, even duplicates, then you could use union all. Here's our previous union example. Two select statements joined as a union, and you can see it returns 4 rows. If I make the union to be an all union and execute it, you'll see this time it returns 5 rows, and one of them is there twice because the duplicated value is no longer excluded. Union all isn't that commonly used, but the reason I include it is to point out that union does have other uses as well. In fact, depending on your DBMS implementation, you'll see some called except, minus, intersect, different kinds of unions that let you include or exclude different values. These vary greatly by DBMS, not used that often, but consult your documentation if you want to use them. The last point to discuss about the use of unions is how you sort them. When using a union, only one order by clause can be used. And it looks like this. You have your select statement, union, followed by subsequent select statements, as many as you need, and then only one order by clause. Let's take a look at the code running in the IDE. Here's our SQL statement, 2 select statements, union and order by, and if I execute it, it returns the ordered results. Now, if you do try to specify 2 order by clauses, SQL will throw an error because it really is generating one result set, and you can only order by that one result set. Okay, one final look at select. Select column always comes first. From table, as many tables as you need, with the join on statement if you need that and if you're using ANSI SQL. Group by, having. If you have multiple select statements, this is where the union goes. You actually can join SQL statements that have aggregation in there using group by and having if you want. Each one is a separate block. Union separates each one. And after all of the SQL statements and all the unions comes one order by statement. Let's summarize. Unions are used to combine one or more queries, and each query must be separated by the word union or union all if you want to include duplicates. If you're using order by, it must be specified after the final query. And some rules about using unions. All queries must have the same columns, although they need not be in the same order. The truth is the types don't have to be the same either. So if one is a character type and one is a variable character, or one is a date and one is a date time, the DBMS will handle that for you. They need to be compatible types, and then union will join the tables and return you one combined result set. For the last 13 lessons, we've used various statements and techniques to get rows out of database tables. Now we need to discuss how to get those rows into tables in the first place. Lesson 15, Inserting Data, introduces the insert statement and demonstrates the safe and unsafe way to use the statement. We then look at inserting query results using insert select and how to export table rows. We've spent the last 13 lessons showing you ways to get data out of database tables, combinations of select statements, joins, subqueries, unions, and more. What we haven't talked about yet is how you get data into the table in the first place. And so in this lesson, we're going to focus on inserting data into a table. To insert rows in a table, you use the insert statement. Insert requires, obviously, that the new column values be provided. And optionally, you can also specify the column names too. Let's look at a few examples. This is a really simple insert statement and one that I plead that you never actually use. Here, insert into customers, and it's listing all the values for the various columns. And if you executed this, it will say one row added, and you have a new row in the table. You'll see it specifying strings for some values, nulls for the others, But do you have any idea what those nulls are for? You don't, because we're not listing the column names. Now this is allowed. This is actually a valid and fully legal SQL syntax. It's also really dangerous. Because if you insert a statement like this and someone changes the table or reorders columns, you're going to put data in the wrong column and not even know and mess up your data integrity. This type of statement is very, very dependent on the order that columns appear in a table, and you shouldn't ever rely on that. Here, this will only work if the first value matches the right first column, which is probably going to be customer ID, second customer name, and so on. And so while syntactically valid SQL, this is generally a really bad idea. This is an alternative and a much better way to write your SQL. Here, the table column names are explicitly listed. So insert into customers, and every column name we want to put a new value in, and then values lists all of the columns. This is much safer, because if it so happens that the column ordering in the table does not match this statement, it'll still work. It doesn't matter. The other beauty of this format is you can eliminate optional columns. For example, we're not providing a contact in email, and so I'm putting null values there. The truth is, I didn't need to do that at all, and I could have just ignored those altogether or put null elsewhere. By specifying the column names, you have a lot more control, and this is the right way to write insert statements. These insert statements will only ever insert one single row, and you specify the values for each of the columns. Here's one final example, and this time eliminating any of the rows we're not using, and you can see it doesn't make a difference, it still works. If you were using the insert format without column names, you would have to list values for all of them, or it would throw an error. Insert is usually used to insert a single row, but insert can be used in conjunction with select to insert multiple rows. What insert then does is execute the select statement, and whatever gets retrieved gets inserted. This is called an insert-select combination, and the select obviously must return the number of columns needed by insert. Column names need not be the same, types must be compatible. Here's an example. Here, the select statement at the bottom is retrieving customer information from a table called customer new, and it is inserting all the rows that were retrieved, however many they are, into our customers table. Now you'll notice that here the column names match perfectly. There's a customer contact, customer email, etc. in each table. That actually need not be the case. What's more important is whatever is first in the select column list matches whatever is first in the insert into column list, and so on. If you are importing from another table, it's very likely column names won't match, and that's okay. As long as the data types are compatible, that will work, and this will select all rows and do a bulk insert operation into your table. Occasionally, you'll want to do the reverse. Export all data from a table into another table, and you can do that with select into. Here, select star into customer copy from customers. This will simply make a copy of all of the rows in the customer table and save them in a new table. Now this is using select star, so it's going to retrieve all rows. If you wanted a subset of the columns, you would just do select column list, and those would get inserted into the new table. It's worth noting that operations like this could be security restricted. Depending what database you're using, if you're using a client-server DBMS, you may find that the administrator of the database allows select operations, but not batch operations like this. And database administrators do have that level of control and security granularity. If you do run into a security error and says you don't have rights, that's the reason. Let's review SQL data insertion. The insert statement is used to insert a single row in a table. If you want to insert multiple rows, use insert select. The select statement may return 0 rows, but it may return 1 or more, and whatever is returned gets inserted into the table. If you want to export data from one table to another, use select into. A couple of best practices. As already noted, when you're using insert, specify the column names. Even though the insert statement doesn't require this, best practices dictate that you do so. And finally, if you are exporting data using insert select or select into, don't use select star, use the explicit column names there as well. Lesson 16, Updating and Deleting Data, teaches just that, how to update and delete table rows. We look at both the update and delete statements, talk about how easy these are to use and how easy they are to mistakenly use. And we look at some best practices designed to prevent accidental data changes or deletion. In Lesson 15, we looked at inserting data into a table. Here we're going to look at how to update and delete data from a table, starting with update first. Now, before we talk about update and delete, one really important warning. SQL unfortunately makes it very, very easy to update and delete the wrong rows. When I show you the syntax, you'll see why. Keep in mind that when you're using statements like update and delete, there is no undo button. And so you better check your statements very, very carefully, especially the where clause. It is very, very easy to mistakenly update every row when you meant to update one, or delete all the rows when you meant to delete one. To update a row, use the update statement. Update gets past the table that you're updating, and then set is used to specify name equals value pairs for each of the columns being updated. And perhaps most importantly, the where clause. The where tells it what row you're going to update, and if you omit that where clause, your DBMS will very reliably update every single row in the table with the updated data. And again, there's no undo button. Here's a simple example. It's updating customers, and it's providing an email address for customer ID as specified. Now notice that where clause. That's really, really important. If that where clause had been omitted, every single customer in the table would now have the exact same newly set email address, which is probably not what you want. This is why in update statements, we typically use the primary key for the where clause. And it's another good reason why all tables should have primary keys, because that's the only real guaranteed safe way to ensure you're only ever updating one row and one row only. To update a row and update multiple columns at the same time, again, update table, set, and this time a comma delimited list of name equals value pairs. Here there are two being provided, and again the where clause telling it exactly which table you want to update. Let's look at one last example, because this one isn't intuitively an update. If you want to delete the value in a column for a row, that's actually not a delete operation, because a delete deletes the entire row. If you want to delete the value in a specific column for a row, you want to update it with null, and null sets it back to no value. In this example here, update customers, set customer email to null for the specified customer ID. Rows are deleted with the delete statement, and the rules for how you use delete are the same as how you use update. Delete takes the name of the table to be deleted, and a where clause to tell it which rows you want to delete. And again, if you omit the where clause, every single row in the table will be deleted. If this scares you, it should. Many developers have lost a lot of data by not being careful with the where clauses. In fact, most of them have gotten in the habit of testing their where clauses with select statements before using them with update and delete. And so they don't ever type a where clause in an update or delete statement. They create a select statement, make sure it functions properly, and then edit the select to be an update and delete without touching that where. That's the only way to be safe. Here's an example. Delete from customers, where customer ID equals a specified ID. If that where clause was not there, every single row in your table is gone and you will have an empty customers table. Update and delete are pretty scary statements, and you have to be used with care. Update is used to update one or more rows in a table, and delete is used to delete one or more rows in a table. They both take where clauses, and the where specifies which rows were affected. You must specify that where clause or all rows will be deleted. So your best practices? Whenever possible, use the primary keys for update and delete. That is a really safe way to ensure you will never impact more than one row. As I said before, test the where clause with a select. This way you know it works and you can look at what it's selecting, and that will tell you what will be updated and deleted. And finally, and this is an interesting one, foreign keys can help prevent accidental deletions. Now let's talk why briefly. If you think back to our lessons on joins and related tables, you'll remember that a foreign key is a key that has values in it that are the primary keys of another table. If you try to delete a primary key that is in use by other foreign keys, the DBMS will throw an error and block it. It won't let you. The DBMS requires, for example, that you first delete all order items before you delete the order to which those order items are associated. If you try to delete the order without the order items, then you'll have orphaned records there, and that will violate referential integrity. Same for orders back to contacts. And so you should be using primary foreign keys anyway, but an extra advantage in using foreign keys is they will prevent you from deleting rows that actually are still in use, and they will help maintain referential integrity. This is our final lesson, lesson 17, where to go from here. Throughout this series, you've learned the SQL that is most used day to day. In this lesson, we look at advanced topics that are beyond the scope of this series. The intent is familiarity rather than expertise. I want to make sure that you understand features like stored procedures, triggers, constraints, and transactions exist, so that you know when you need them, and you'll be able to review your DBS documentation to learn more. We've used lots of SQL statements so far. Select, insert, update, delete, and lots of variations of those. And the truth is, those are the statements you're going to use primarily. There are a lot more SQL statements, most used for administration or for creating tables, views, and more. And they're beyond the scope of this series, but I do want to briefly go through some important ones, less so that you should know the syntax, and more just so you should know what they are. Because if any of these sound useful, then refer to your DBMS documentation and dig into them. We'll first look at the statements used to create, update, and delete tables themselves, not the rows within tables, but actually tables. Even if you use a tool to graphically design your tables, under the hood, this is actually being done using SQL statements. To create tables, as you'd expect, the command is create table. Tables are updated using alter table, and to remove a table, it is dropped. Now, the exact syntax for create, alter, and drop are very DBMS specific, and they can also be security restricted, but in corporate networks, this may in fact be the case. Users may be given permission to select data, insert, update, delete, but they may not be allowed to actually change tables or manage them or administer them. And so you may need administrative rights or ask for permission to do so. This is what a create table statement looks like. This is in fact the table that we've been using for products throughout our lessons over here. And here you can see it's defining a table called products. There are 5 rows, and the data type is defined for each. The first 2 are character 10, so they allow characters up to 10 characters long. The third allows a name longer. The price here is a decimal, so it's a numeric value, and other DBMSs call this money or number. And the description is variable, up to 1,000 characters. The char, the character, will always be 10 or 254, regardless of how much space is used. The Wildcard, the variable, is saying you can store 1, 2, 3, as many characters as you need, up to 1,000 characters, and it will only take that much space. You'll also see on the side that some of the columns are specified as not null, and one is null. Not null means this column will not accept null values. Those are required columns, and the description here is null. Here's another example of a create statement, this time creating the order items table, and this is using a default value for quantity. And again, this is supported by most DBMSs, but as I said before, the exact syntax for create table does vary quite differently from one DBMS to the next. But here it's saying if you add an order item and neglect the quantity, default it to 1, it puts that number in for you. If you want to change a table, alter table, and here we're dropping the vendor phone column. And alter table is also used to add primary foreign keys. Here, alter table vendors add constraint primary key to vendor ID. So this, if you did not create a primary key at table create time, the alter table is being used to add a primary key. And this is in fact how most users create their keys. And if you look at the scripts that were used to create the examples in these lessons, if you follow along, that's exactly how all of our examples were created as well. a create table statement for each table, and then a series of alter table statements to add the primary and foreign keys. To drop a table, it's simply drop table, and again, no undo. Views are virtual tables. From a select statement standpoint, they look and behave just like a table, but they allow the results of one select to be used as a table. You create them with create view, updated with alter view, dropped with drop view, and as you've seen before with tables, create, alter, and drop can and often are security restricted. In this example here, this is taking a select statement we used earlier on. We used this join, and it's turning it into a view. And so now, if you look at the select statement at the bottom of the page, you can select customer name and contact from product customers as if it was a simple table without ever worrying about the join, because the join of 3 tables is already saved as a view. Right? The select statement, which takes customers, orders, order items, what we created before, instead of using it over and over again, save it one time as a reusable view, and then from that point on, anybody else can retrieve data from it as if it was a table, even though in fact isn't. A couple of things to know about views. They must be uniquely named, so you can't have a view the same name as a table. That would create problems. They can be nested. So if you want to create views on your tables and then views based on views and views based on views based on views based on tables, you can do that. Views don't support order by. It wouldn't make sense because a view, even though it has a select statement in it, behaves more like a table, and tables aren't ordered. And finally, be aware that some, although not most, DBMSs treat views as read-only, which means you can select data from the view, but you can't update it. Most DBMSs, in fact, do allow you to update your views, and if you update the view, they will automatically update the underlying tables appropriately. Stored procedures are programs written entirely in SQL. Now, why would you want to do something like this? Well, imagine you had a really complex process for adding a new customer that involved first checking if they were there or not, and then assigning a customer ID, and then adding a table, and then setting up some default mailing entries and so on. There might be lots of tables and things you need to do. To make sure they happen all and in the appropriate order, you can take all those statements and put them in a single program called a stored procedure. Stored procedures support loops, so you can loop through code, do if statements, they can pass data in and out, and a lot more. They're typically used for 3 purposes. One is security. You may not want users accessing underlying tables, but if you give them stored procedures, you can control the pipeline, the funnel, by which they access those tables. And this way, you control data going in and out. They're also used for simplicity. If you do have a set of complex operations, the odds of them always happening in the right order could be slim. By hiding that behind a stored procedure, users pass in the data, and your stored procedure ensures that everything executes properly. And finally, performance. Stored procedures are pre-compiled and can run very, very quickly. And so for complex operations, there are actually performance gains as well. Stored procedures are very DBMS specific. In fact, I've yet to see a stored procedure that runs on more than one DBMS. They are all very, very different, unfortunately. Before we wrap, I want to quickly go through a few other concepts that you should be aware of. The first are triggers. Now, triggers are interesting. They're kind of like stored procedures, but they're code that executes automatically when an event occurs. So let me give you an example. Maybe you're adding a new customer to your database, and users have this annoying habit of some typing states in full text, some abbreviating them, some uppercasing the abbreviation, some lowercasing, some putting n.y dots, some not putting in the dots. What if you want to ensure consistency? Now, you could try train your users. That's seldom useful. A better option might be let the user put in whatever they want, and you have code on the server that every time a row is inserted or updated, it runs and cleans up the data for you. You'll want this piece of code, probably a stored procedure, to run automatically every time when an event occurs. That's what a trigger is for. Triggers are added to insert, update, and delete operations, and they execute automatically on the server, and they can often execute before or after the operation. They're used for ensuring data consistency. They're used for ensuring validation. They're also used for archiving, because we talked before about the danger in deletes. You could have a trigger on delete that every time a row is deleted, before it's deleted, a copy is made in an archive file. That's actually a pretty common use of a delete trigger. Triggers are a more advanced topic, and again, their use may be restricted by the administrator. They're tied to tables, so a per table per event, but they're a really powerful way of having code automatically execute to ensure that your data, your table and its behaviors are always the way you want. Next up, cursors. Now, as you see in select statements, when they return data, return sets. There's really no way to return one row at a time and loop through them. And sometimes you may want that. Sometimes you may want to get data and then for each record, process it. Maybe if it's based on country, provide different shipping information, or based on last activity of the customer, do something different. There's no easy way to do that in a select because the select just returns a batch of data. A cursor is code that runs on the server that then lets you loop through the rows one by one, the rows meeting a select criteria, select where condition, and then execute code against each row individually. These are used for reporting, for per row calculations, and for data manipulation as well. Transactions are a way to define a block of code that must be executed in its entirety or not at all. Let's look at an example. Perhaps you're adding an order that someone made to your database. So you add the order to the orders table, and then for each item in the order, you add a row to the order items tables. Now, what would happen if something went wrong and the order got entered and the items didn't, or only part of the items got entered? You'll now end up with an incomplete or inconsistent order, and you wouldn't really know. What you would want is to ensure that the entire order is entered properly, the order and the order items, and if not, you want the whole process undone so you can deal with the error, but at least your database is left in a safe, reliable state. To do this, you create a transaction. The transaction block would start before the order record is inserted, and it would end when all of the order items rows are inserted. And then if any problem occurs, it would roll back. Transactions give you, the developer, the ability to manage how rollbacks work. By default, it rolls the whole way back, but you could create save points and roll back to them as needed. Transactions are really important for financial operations where it would be unsafe to have partial or incomplete data saved. Transactions are really all about data integrity, and they're a really important part of keeping data safe and reliable. And finally, constraints. Constraints are rules that can be applied to your table. For example, if you had a gender column in your contacts table and you accept two values, M or F, there's really no way to ensure that users don't put in any of the other 24 characters in the alphabet, as nonsensical as that might be. You could put a constraint in the table that does not allow anything other than the allowed values. Constraints are usually added at table creation time, but they can be applied later as well using alter table. Constraints are very DBMS specific, and they are invaluable for ensuring the integrity of your data. You can rely on users to try to do the right thing, and probably should, but it's always best if the table verifies and checks for you and makes sure users cannot ever enter data that shouldn't be there. And there you have it, some more advanced DBMS functionality. We didn't go into a lot of detail, but it's good to know those features exist if you ever need them. And if you do want to learn more, please refer to your DBMS documentation. In this series, you learned all of the SQL that you'll use in daily database programming. Whether you're running reports, building smartphone apps, or creating websites, the SQL you learned in this series will get you up and running regardless of the DBMS you are using. Those pages are also where you'll find all of the downloadable scripts and examples used in this series. Thank you.